Hello. Good morning, sir.
शक्ति सुनाई दे रहा है?
Yes, sir. Yes, sir.
ओके, तो शेयर कितने बजे करूं? अभी करूं शुरू?
Sir, 11 o'clock, sir.
शेयर
Sir, share आप क्लास सर. अभी
5 मिनट के बाद करूंगा, ठीक है?
Yes, sir.
अदरवाइज क्लियर है, ठीक है?
Yes, sir. Yes, sir.
ओके, फाइन. रंजन कैसे हो?
हाँ जी, बढ़िया.
So who is the session chair?
I think I and Sunil are session chair.
ठीक है, 2-3 मिनट एक्स्ट्रा. 11:30 तक है ना? ठीक है.
हाँ, 11:30 तक.
ठीक है.
अभी I think हाँ
2 मिनट में शेयर करूंगा स्लाइड्स उसमें.
हाँ, अभी तो 11 बजे स्टार्ट होगा. आई थिंक लोग आ जाएंगे और पीपल विल बी कमिंग अभी तक.
नहीं, ठीक है, कोई प्रॉब्लम. So how many parallel sessions are there?
Not sure. I think 4-5 हैं.
ठीक.
Sunil, are you there?
Hello.
Sunil. Okay, you are also
Good
here.
morning. Yeah.
Morning.
Sunil, how are you?
Yeah, I'm fine, sir. Thank you. How are you, sir?
Fine, everything fine. तो कैसा चल रहा है कॉन्फ्रेंस?
मुझे लग रहा है ठीक ही चल रहा है. Yeah.
कोविड में I think it's a great thing.
Yeah. To have it online, exactly. I mean, we had the first experience of our life online poster sessions yesterday.
It is actually it is increasing like anything.
Yeah, that is true.
It is increasing like anything.
I think COVID लोगों ने छोड़ दिया है.
नहीं
ऊपर
हमारे
वालों को छोड़ दिया सब.
we had a 54-year-old businessman, very healthy and no diseases, pre-disease. So what happened to him? I don't know why he went and came back. No symptoms, but uska oxygen went to 93, which is not bad. But he just went to Gangaram and they said you get admitted, you have COVID positive. And 3 days he died.
Oh my God.
वही है. Never know किसको होगा.
Yeah.
और कौन कुछ 80-year-old also कुछ नहीं होता है and 50-year-old passes away.
But if you go to places like Sarojinagar and other places, it is very bad, very bad. You see, nobody uses mask and other things there.
कोई मतलब ही नहीं है किसी को. इनफैक्ट मैं देखा था गुड़गांव मानेसर में कोई बॉदर ही नहीं करता है. कोई स्कूल वूल चालू कर दिया था बस में. थियोरेटिकली बोल रहे थे ओनली फॉर सीनियर स्टूडेंट, बट आई हैव सीन सब बस में भर के स्टूडेंट्स जा रहे थे.
But you have other problems. This farmer agitation is another big problem. There's too much of traffic jam on some roads.
मैं देखा था गुड़गांव मानेसर में कोई बॉदर नहीं करता है. कोई स्कूल वूल चालू कर दिया था बस में. थियोरेटिकली बोल
IIT का क्या हाल है? ठीक ही चल रहा है?
हाँ चल रहा है सब.
कुछ फंडिंग मिल गया वो IOE वाला?
I have no idea. इतनी जल्दी थोड़ी होगा वो. That will happen so quickly.
Yeah, I think not that much of money will come because he mentioned it last meeting that I don't have much money.
ठीक है whatever.
I think
Possible.
COVID में we have started learning how to live with bare minimum.
Yes.
कपड़े तो चाहिए नहीं, खर्चा ही नहीं है. ऑनलाइन सारा ऑर्डर करो, खाते क्या है अब? मटन मछली सारा बंद. But if a person contracts this, I think it has a lot of problem. You see, Tapan Sarkar ko his kidneys have failed in US. So he's under dialysis because after he tested positive, he was given good treatment in New York. उसके बाद ठीक हो गया. Suddenly ये problem हो गई फिर उसको. He went to Peru and contracted it again. And he's on dialysis now in New York.
से काम करते क्यों है पता नहीं.
अब ये उनका बीमारी है, travel.
Shakti, are other people from CARE joining or some? I think some of the students are joining, right? एक बार check कर लो.
एक्चुअली सर ऐसा है कि जो आज का वो है सिंपोजिया का लिंक ना सर, वो दे हैव टू यूज डेलीगेट लिंक. So I think they are not visible in this participant list.
Oh, okay. हाँ, so they are already there anyway.
Yes sir.
कुछ लोग तो हैं और ना. हाँ.
Yes sir. जैसे सौम्या ने ज्वाइन किया है वो देख रही है लाइव, बट her name is not visible in the participant list.
Oh, okay. हाँ ठीक है. I know that वैसा कुछ है. Something like that. Okay, Sunil, so should we start?
Yeah,
We can probably wait for a few more minutes because in between anyway we will get some time.
So today is the last day?
Yes, today is the last day, yes.
You see these webinars and international events, virtual events, it has, exponentially increased. Every day there are 10 notices.
Yes. I have done 3 PhD vivas recently, last two months में 3 PhD vivas over the internet.
कहाँ
एक और
कहाँ
होगा,
किया?
एक ISM धनबाद, एक DTU, एक
Dhanbad one is
somewhere else.
every month a PhD.
हाँ.
Every month.
Unfortunately, I've seen that, when you ask them questions, even very simple questions, even what they have done themselves, what is written in the thesis,
They don't know.
they don't know things properly. Actually, too much simulation. Simulation, more simulation, this graph, that graph. Thesis has 70,000 graphs and structures and चीजें, but basic चीजें जो है वो confused हो जाते हैं. Oh, I see Venkat Vanukuru has also joined. Good morning, Venkat.
Good morning, Dr. Ananjan.
Morning. Seeing you after a long time.
Yes.
Good. Professor Aniruddhan is not here yet. Is he there?
This is at 11:30, so.
So actually after 12:45 we have this lunch break.
Yes.
So this session we have got some time actually because
Yes, we have a lot of buffer.
yeah, one oral presenter dropped out.
No, you can give me 5 more minutes, no problem.
Yeah,
Which presenter dropped out?
one more oral presenter was here. I think from 12:45 to 1. So
Oh, okay.
So that way we have got 15 minutes here. Yeah.
We have some extra.
5 minutes, no problem.
Okay, but anything, I think we can start now.
No problem yet.
Okay, so we'll start it. So protocol, please share your slides.
Yeah, just check whether they come okay. एक minute.
Yeah.
Is it okay?
Yes, it's fine.
Clear? Okay. So what time you want me to start it?
So yes, we'll start. I'll just introduce the speaker as is custom. So just a minute. We all, of course, so just officially welcome all of you to this session of the conference. And the first speaker is Professor Shibban Kaul. I don't think he needs any introduction. We all know him.
Yeah, you give me 2 more minutes. Better. No, don't. It's okay.
Just for the normal tradition, I just mentioned that he is, as you can see here, he is Emeritus Professor at KR IIT Delhi, and he has also held many other positions: Deputy Director at IIT Delhi, Deputy Director at IIT Jammu, Chairman Astra Microwave Products. He's a Life Fellow of IEEE and many awards. So one of his expertises is in RF MEMS. He is very knowledgeable in this area. He has done a lot of work in this field. So I am sure you'll all come to know good things about the very interesting area of RF MEMS technology. So Professor Kaul, please go ahead.
Thank you, Ananjan, for introducing. And the title is Radio Frequency Microelectromechanical System, Micromechanical Technology. basically, I'll give you a glimpse of the work which we did last 1 decade at CARE IIT and what we are doing currently. Now, this is basically contents standalone RF MEMS switches which we did long ago, the novel RF MEMS switches and phase shifters, multi-frequency phase shifters, concept of lateral MEMS for improving reliability, and DGS and mathematics we started with MTech students, and something is coming up now in this area. And lastly, center frequency bandwidth tunable MEMS bandpass filter for 5G application. We did recently make 1 or 2 of these filters, so I'll share these things with you. Finally, a brief summary. If you look at RF MEMS switches on the left-hand side, on the left-hand side is basically a ohmic contact switch. We have a singly supported cantilever, and then depending on the actuation voltage, we can bring it down as shown below. So the on state here is the wave graph which is shown below, and in this state is off, no electromagnetic signal passes through this particular one. So this is a ohmic contact, and normally the performance is from DC onwards. Well, as on the right hand side is basically a capacitive switch. We have a substrate here, and we have these conductors, and on top of it the green one is a dielectric, silicon nitride, silicon dioxide. Then we create a doubly supported cantilever, and whenever we apply DC voltage to this cantilever with respect to the ground, and the membrane is pulled down, so we get large capacitance, and this can be calculated from epsilon AD, and it doesn't allow electromagnetic waves to propagate. So this is the off state, and this is the on state when there is no actuation voltage applied. So this is basic ohmic contact versus capacitive MEMS switches. So when we started the work long ago, we worked on standalone RF MEMS switch development, and so the investigations which were carried out, most of the work in our department is done by students. As Ananjan mentioned, I'm not an expert, I'm just guiding them. So extensive investigation on MEMS, metal contact switches. If you want to perfect it, you have to do profile analysis, you have to do mechanical response, electrical response, transient response, loss analysis, linearity, power handling, temperature sensitivity, reliability, and size optimization. All these were done with a nice PhD student who did all this work so that the device works properly, and this can be used for other circuits. So this is the schematic student came up, RF MEMS DC contact switch. We have basically an anchor, and then we have the metallic body, then we have dimples here. You can see the dimple, which basically makes the DC contact on off. We have input here, we have output here when the membrane is pulled down, and the substrate which was used for fabricating these is 635 micrometer epsilon R 9.6. So you go to Coventry where we had the tool there. So there's a cyber architect. So we create this structure here. We have an anchor here. Then we have lever 1, lever 2, lever 1, lever 2. Then we have beams. So another beam, then dimples. So we create this structure, then analyze, and we find out which parameter to be adjusted depending on the performance of the switch which is desired. So this is the first fabricated switch. This is the switch, and these bridges are basically these coplanar grounds, basically to make the potential same. So we have to put them periodically, and this is the dimple. This is the DC bias line, and this is the return path. And this is DC bias line, that's the return part, and this is the SEM of the switch. You can see these are the dimples which were, and the air holes here are just to take care of the air damping necessary. So these were characterized. We did this is the SEM, this is the mechanical frequency, actuation voltage. All these can be controlled by changing the parameters of the switch. The switching time 89 microseconds, release 143. Then microwave performance, return loss 22.5, insertion 0.42. Isolation not very good, 19 dB. So this is the basic switch which was done, and then using this switch we made SPST high isolation switch by combining 3 such switches. We made SPDT switches. But the switches are quite bulky in terms of when you talk of the microelectromechanical systems. So they can be used as standalone. They're highly reliable, but not good for making phase shifters and other components using this switch. So this is the transmission loss and the return loss of this. Based on this and equivalent circuit, you can convert them into the equivalent circuit formulas for the switch, and you can get capacitance, resistance, inductance. And once you have the equivalent circuit, you can cascade them series, parallel, using the simple ADS circuit simulator tool, and to develop more complex switches required for phase shifters and other applications. So this is a miniaturized SPST switch which was thought of, and if you look at this is a human being like push-ups. These are two hands, and this is the anchor, and these are basically perforated holes here. Very small switch. So this is very stable, and if you look at switch area 0.011 millimeter square, and including the transition, it is 0.09 millimeter square. So this was properly designed, and using this concept, so we developed several types. This is basically SPST, SP3T. Now 3 of them are combined. Each time you have a transition at the input output. Then 4 SP4T, 6T, 7T, 10T, 11T, 14T. Now the size of the switch is such that we cannot go beyond 14T because the periphery accommodates only 14 such switches. But we need also 16 switch, so we have to develop a different type of switch for realizing SP16T. So the performance of these over 0.1 to 26 gigahertz, this is the S11, S21, isolation, and most important thing is size. It's very, very small. So if you use them in phase shifters, you can probably get a small chip, which 3 by 3 or 3 by 5 millimeter, which will be a complete 5-bit phase shifter. So that's the advantage of this switch. The first one is not that useful for the development of integrated phase shifter. So performance of this on the network analyzer for SPST, 4T, 6T, so on up to 14T is illustrated in this particular view graph. Now to make SP16 switch, we remove those 2 anchors and we have a simple inline switch. We have just one anchor and then perforated holes, and this is the stopper, just one. And this allows us to have 16 of them. So first we test it less than 0.5 dB. So it's 0.38 dB at center frequency, S1 125 dB, isolation greater than 18 dB, which is more than enough for the switch application. Then we cascade them. It's a very complex geometry. We have now 16 of them in a periphery, and then we draw the equivalent circuit of them, and then there are some interconnecting lines, and we have a common point. So make an equivalent circuit of this, and this is the equivalent circuit of the switch. Now we can use circuit simulator to further optimize the transmission line lengths as far as the SP16 switch is concerned. So these are the microwave performances. We have insertion loss, we have the insertion loss for various ports, and they're less than 1 dB at the center frequency for most of them. But please remember, this includes also the transitions. This includes the transition loss, which is basically two transitions, input-output transitions for this particular switch. The isolation in the off state is better than 14 dB. One can improve it, but it's a trade-off between the switch size and also the isolation. And then we did reliability up to 1 billion cycles, 25 degrees centigrade. You can see the contact resistance changes. It doesn't drastically change, but definitely changes, and also changes with power. And this is, I think, acceptable. Later, we have increased this one. This was at the time when we wrote the paper, to 10 billion cycles. It still performs quite well. Now, utilizing these in phase shifters, we have 2 main configurations. One is switch line phase shifter, which basically we have a reference arm, and then we have a delay arm, which is longer than that. And we can use 2 SPST switches here or SPDT switch here. And depending on the path length, we can have beta L1 as the phase shift here and beta L2 as the phase shift here. Differential phase shift is beta L2 minus L1. So that's the principle, and we can use this equal to a bit size is 22.5 or 11 degrees. So we can make different bits and cascade them to make 4, 5, 6-bit phase shifter. On the right hand side is basically distributed MEMS transmission line. It's a coplanar line, and then we put these MEMS bridges and calculate the spacing and the width of the bridges so that we can have variable capacitance on this line, and we can develop an analog phase shifter. These are the 2 most commonly used phase shifters for the application and the phased arrays. Now looking at the switch line, we have now the earlier standalone switch. We can put them here and have path difference 11.25, 22.5, 45, 90 degrees, 180 degrees. All these bits were separately made numbers and tested. So this is the performance of different bits. This is the lowest bit, This is the second, third, fourth, fifth bit. And I think the performance of all these bits is perfectly okay. And then we have to cascade them. So we cascade all of them and it becomes a chip of size 11.4 into 4 millimeter square with a return loss better than 15 dB. And this is average insertion loss is about 5.5 dB over 17 to 17.5. Now the drawback here is, to get one phase state, you have to switch at least 10 switches, and switching 10 switches means reliability is an issue in this particular case. Now we thought of a new architecture where we use SP40 switch, SP40 switch, SP40, and then SPDT switches. So if you want to get phase shift, so we have 4 bits here, 4 bits here, 2 bits on the right hand side. So to switch to a particular phase state, we need 1, 2, 3, 4, 5, 6 switches. So in the previous case, we need minimum 10 switches. Here it is 6 switches. So we expect that this will be more reliable because less number of switches to be switched. Obviously, reliability will go up. So we designed a single bit, then the second bit. So it gives you 4 phase bit states. This gives you 4 phase states. And then this gives you 0 and 180. So like that, these are the bits. So important thing here is the junctions have to be optimized for better impedance match. So this is the view of the junction, how it is optimized so that return loss, insertion loss is minimized. So these bits were individually tested and cascaded together. So you get a chip of 5.17 by 3.19 millimeter. The only additional work you have to do is these blocks, block A and block D. These are 2 transmission line pieces, which basically are to be adjusted so that impedance matching is there between all the 3 bits. This can be done on a software tool. And once this is done, then you can get better than 20 dB return loss for all phase states. And the insertion loss is also less. Earlier was almost 5.5, it's around 3.5. So it shows 90 dB S11, S22, and 3.89 over 13 to 80 gigahertz. And the phase error is very less, 1.14 degrees. That too for 258. For other bits, it's much lower. So this is a very good phase shifter and size is reasonably good. So this is how it is put. This is the phase shifter bit, and then you connect it to the housing, both input output connectors, and then attach the control circuitry and then put it here for testing the reliability. This was done at Astra Microwave, and in 2015 IEEE transaction gives the details of the reliability analysis of this particular phase shifter in detail, and this worked perfectly well. This is the cold switch test, and the average phase error max 4 when you go to 10 million cycles, and the insertion loss increases from 3.8 to roughly about 5.5 at 17 gigahertz. Now we also had SP40 and SP80. We can develop very small 3-bit, 4-bit phase shifters. So what we do, we use this 40 here and we use 80 here. Then we have 4 branches here, and we get 3 bits, that's 8 states, by moving these MEMS bridges over these transmission lines. So we can get 3 bits here, same principle here. Instead of using SP40, we use SP80, and we get basically 8 states, 16 states here. And this is published in IEEE Journal of Micromechanical Feb 2018. A lot of details about the performance characteristics of these, but they're very, very compact, few millimeters, 1 or 2 millimeters by 1 or 2 millimeters. So you can make a chip phase shifter giving 3-bit and 4-bit. This is the performance of both these phase shifters, 34 or 35 gigahertz central frequency, and it's quite small, and measured and simulated results match quite well for different phase states. Next is SP16 switch, and we can have one SP16 switch, one SP16 switch. Now there's no cantilevers on these are all delay lines. And this phase shifter size 3.62 by 3.37. And so we can use these, and the interconnects have to be optimized so that the corners have to be optimized in this one. And this is also published in IEEE Journal Micromechanical August 2018. So this works very well, and you don't have the beams on each of the transmission line in this one. So it's much more reliable compared with those structures. And these are the major results for 18 to 26 gigahertz, 18 to 26 gigahertz for this SP16T based phase shifter. And this is the phase response, 2.3 degrees the error at 25 gigahertz, which is well within the expected response from these phase shifters. This is the cold switch reliability. On the right hand side is average phase shift, left hand side is average insertion loss, and 3 power levels. We have tested this up to 1 billion cycles. This was tested at Astra Microwave, Hyderabad. Now, using this SP40 concept, SP40 switch concept, we can now make a multi-band phase shifter. We can have 4 DMTL phase shift, distributed MEMS phase shifter. This operating 18 to 19, this operating 20 to 21, this is 22 to 23, and this operating 22 to 4. So we can switch one of them and then use it as a phase shifter. So you don't have to every time make a new phase shifter. This concept will help you to make phase shifter at different frequencies. So this is the layout of this very complex layout. So these are the cantilevers, which basically give you analog phase shift from at 18 to 19 band. This is for the other band. This is 22, 23, 20, 21, and this uses SP40 switch at this point. It's very complex layout, but it works. And we extended the frequency of this to 60 gigahertz by using the same SP40 switch here. And this works at 60 gigahertz, this is at 35 gigahertz, this is at 25 gigahertz, and this works at 17 gigahertz. So these are excellent in terms of the size and the reliability. So we tested it 16 to 72, this is S21, and this is 24 to 25, this is 34 to 35, and then 50 to 60. This is S21, this is S11, and better than 10 dB for all the phase bits. And this proves that the concept works, so you don't need to make different phase shifters. One phase shifter works at 4 different frequencies. We can increase number of frequencies, the chip size will increase. We also looked at one of the major problems in this capacitive MEMS switch is stiction, because when the top membrane comes down in contact with dielectric, it sticks. So we thought, let us look at the lateral SPST switch where there's no top-down motion, it's in plane motion. So we use a spring loaded structure here, and when we actuate it, this spring is pulled this direction. So that makes a contact here. So insertion loss of a typical switch is about 0.13 dB, return loss 19 dB, isolation 26 dB. So this concept was extended to have SP40 switches, 4 switches here, and then we also did SP70 switches, and this is published last time presented in the IMAR conference, details of this, including reliability and its bandwidth performance, and it's much better than the capacitive MEMS switch. So this was already, but we didn't go beyond 7 because it's not possible to accommodate these springs into this structure. Now, very recently, through MTech students, Chaitanya is one, and then Pranab is a PhD student, we thought of using the DGS, defective ground structures and metamaterials. Can we do it? And this is published by Microwave Journal, 3 articles in September 2020, innovative concepts in MEMS switches with metamaterial contacts. There are a lot of companies working in US in this particular area. So we thought before we publish, we secure the patent, and I'm glad that September 2020, we got the full US patent on this particular technique. So here, this is the concept. We use basically a signal line, which is serpentine. And if you use this serpentine signal line, your actuation voltage will be less. But you will have a very narrow isolation curve. Bandwidth will be very small. So we add these DGS structures. They need not be symmetrical. They can be asymmetrical, 1, 1, and 2, 2. And the moment we apply these DGSs, our isolation curve broadens, but insertion loss also reduces. So then we put secondary switches on top of them. And these secondary switches, if we adjust the height, the insertion loss comes back to the same thing, and we can adjust the heights so that we can have the isolation peaks anywhere from 75 to 170 gigahertz. And also we can broaden it. So a lot of permutation combinations can be done. So this is how we can move the isolation peaks wherever we like using the DGS and the switch, secondary switch on the DGS. Now, another concept which we have put in the patent is this CASIMIR force is well known. When you have 2 metal plates, there's a force between them. It's called CASIMIR force, and the structure has to be like this. We have to have a metal, dielectric metal, and if we create a metal 3 here, a metamaterial, so that it gives negative or 0 permittivity, we can generate a repulsive CASIMIR force. So when the stiction force is there, so this negates it, so you don't really get stiction if you do this kind of thing. So first is to create a structure to do this kind of thing. So we attempted a structure like this. We created a unit cell in the signal line, And analyzing the S21 of this structure, we can get really negative permittivity and very close to this. Over a broad band here, we have the permittivity very close to 0. So you have this insertion loss, and you can have broadband isolation. You can play with this. And this is just a conceptual state. We did a polymumps run for this, and it works. And now some RF things have to be done. So the last part is, very recently we did tunable MEMS bandpass filter. If you look at a transceiver, we have an LNA, we have switches, we have a bandpass filter here. Switches are already done. Can we make a bandpass filter which is tunable in terms of the center frequency, also bandwidth? And this is for 5G applications. So we used basically array of series switches, array of shunt switches, developed its equivalent circuits, and together when we connect it, we can have the same effect which I mentioned just now. So this is basically 4 series switches which we described earlier, and this is the 4 cantilever switches, which is the shunt switches. So we put them here, we put them here, we put this here, we put this here, and together this becomes a tunable MEMS bandpass filter. And these are the responses. You can see there is a narrow band. We can make it broadband at the same center frequency, or I can change the center frequency, and the simulation and measured results work perfectly okay. First graph is 27.4, second is 28.3, third is 29. And this is just published in IEEE transaction on 10th November. It is just in the open access, so you can have a look at it. So this is very interesting application for moving the center frequency finely using this particular technique. So these are the, as I said, there are a lot of companies working. So we secured all the 3. One is the phase shifter. We have got the patent granted in 2019 now. All the switches which I reported, it is June 2019, after almost 1 or 2 years. And this microelectromechanical thing which I said, we just got it in September 22. There was a legal battle with one company. Finally, we got it. So IP is now secured. And just have 1 or 2 chapters in this book, which is edited by KJ Vinoy. And we wrote a book called Radio Frequency Micromechanical Switching Networks. So you can have details about all the techniques which I mentioned in this particular book. So I think I'm on time. And summary is, we worked on new switches, we worked on phase shifters for reduced size, low cost, less friction, improved reliability at microwave millimeter wave frequency. Of course, some projects are going on with Ananjan now at 94 gigahertz. And we need research to continue before these can be commercialized for 5G IoT application. One of the things is packaging. The second thing is very low cost. Thank you for your attention. If you have quick questions, I can answer. But before I close, I would like to take this opportunity to thank my colleagues at the Center for Applied Research in Electronics, all students. The major part of the work was done by Skomal, who is now IIT Palakkad. And now our new group in charge is Ananjan, who is supportive, because we have some projects from DRDO where 94 gigahertz switch is there. And to all my colleagues in the Center for Applied Research in Electronics, Astra Microwave helped us, RCI helped us, Space Application Center, then GATEC, Sitar, SCL. So we have been working with practically everybody. So this is the outcome of the work, which is a joint research with so many people. And finally, to Synergy Microwave, who helps us in filing patents. It costs a lot of money in US. So they have kindly agreed to do that. And so their contribution is also acknowledged. Thank you very much. Any quick question, I'll be glad to answer.
Okay, so thank you, Professor Kaul, very much for your talk.
I'm on time.
Since we have a little time, so any questions from the students or other participants?
I still left 3 minutes for you.
Yes, anybody has any question? Anybody wants to know something about?
Anyway, you can go through it. Slides will be available on they are recorded, so it will be available. In case there is a question, you can email to me. I'll be glad to answer it. There's no problem. But if you have it right now, I'll be glad to answer it.
And there may be participants who are not visible on the screen here. You can also ask any questions if you want. You can use the chat or just speak out. Okay, I think we are good. So
this presentation will be there online for about a week. So if anybody has any questions, you can email to me. There's no problem. I'll be glad to answer. No problem. Is
okay.
it true,
So,
Anand, there for 1 week?
yes, correct. That is correct. Yes.
And if somebody needs the presentation, they can email to me. I can send it. There's no problem.
Okay, so we will then thank the speaker for the call. Thank you very much for your talk.
Thank you, Ananjan. Thanks. So should I log off now?
Yeah, you are welcome to continue, but I think you can stop sharing the screen.
Sure, I will do that.
And then we will move on to the next speaker.
Okay. I will have a cup of tea then come. Thank you. Thanks, Ananjan.
Okay, thank you very much, Oscar. Sunil, should we move on to the next talk then?
Yes.
Okay. So, Professor Aniruddhan is there, of course.
Yes.
Can you hear me, Professor Aniruddhan?
Yes, I can. Just 1 minute.
Okay.
For some reason, my rear video camera is turning on. Just 1 minute. Yes.
Yes. Good morning.
Okay.
Nice to see you. So you are ready to, yes, please share the content.
Yes.
And,
yes. Are you folks able to see?
yes, I think it's visible. So I will just take 1 minute and So okay, so all the participants, we will now proceed to the second talk. So the speaker is Dr. Aniruddhan from IIT Madras. So Dr. Aniruddhan is an assistant professor there, and he got his PhD from the University of Washington, Seattle. And those of you who are familiar will know that this is one of the major places where developments in RFIC and these areas are going on. Subsequently, he has been continuing his research work on RFIC circuits, basically on-chip circuits at IIT Madras, and especially for 5G applications. So Professor Anandan is very well known in circles where 5G research is done, and we are glad that he is here today to share his knowledge with us. This topic which you see before you, 5G new radio, the India perspective. So Professor Anandan, please go ahead with your talk. Thank you very much for having you here.
Yeah, thank you, Professor Ananjan. The title of my talk today is 5G New Radio, the India perspective. So there are two parts to this. The first part is the 5G New Radio part. So there are some things which are different as far as 5G is concerned compared to the previous generations of cellular telephones. And the second part is the India perspective. So there is something specific related to India in the new standard. So I will cover these two parts in the first part of my talk, in the first half of my talk. In the second half, I will present a particular RFIC research work that we have done, which is related to one part of the 5G new standard. So I think I've already told you what the outline of my talk is going to be. Introduction to 5G, followed by what is specific to India, then the research on full duplex wireless communication, and finally, if we have time at the end, I will talk about a little bit about the 5G India testbed, if we have time. So if you look at the earliest generations of cellular telephones, so if you look at 1G in the 80s, you are looking at a system that primarily gives you voice connectivity with mobility. So it was based on a frequency modulated signal. It was almost completely analog. So there was no concept of security. And you can work out the effective speed to be a couple of 2.4, 2.5 kilobits per second. Then in the 90s, you had the second generation 2G cellular communication, which is basically GSM. And for the first time in GSM, you had digital signals that were used for voice transmission. So basically, digital signal processing, the power of DSP was used, was harnessed to enable better cellular communication. So obviously the data rates went up. So then it led to 2.5G, what is called edge, where you could transmit a few hundred kilobits per second of data. Then in the 2000s, you had the 3G revolution, which was called UMTS. And you will find that there was a parallel path taken by with two approaches. One was UMTS. The second path was what was called CDMA 2000. Qualcomm had developed code division multiple access and really brought to power the digital signal processing in a different way. So these were two, you could call them competing standards. And for the first time, you had high-speed data, several megabits per second coming on your cell phone, and you enter the smartphone era. And because I'm going to talk about the Indian scenario, I also want to point out that in 3G, for the first time, China came up with a particular version or one small part of the standard called TD-SCDMA. Then starting from approximately 2010, you had 4G. Again, you had two competing standards, LTE and WiMAX. But due to various reasons, WiMAX fell by the wayside and LTE was adopted by almost everybody. And the latest versions of the LTE standard can support up to 100 megabits per second through something called carrier aggregation. And for the first time, voice was not seen as separate, it was sent as data packets, so you are looking at voice over IP, and security became a big concern, and you had options of streaming, high definition video right to your cell phone. So now we come to the starting from 2015 onwards, people have been researching 5G systems, and companies have been trying to standardize what 5G looks like. So primarily, the 5G, so-called 5G new radio, is going to have three major portions. The first portion is also called Enhanced Mobile Broadband, or EMBB. So you are talking about peak data rates of 10 to 20 Gbps. Okay, and at the same time, it is also going to support very high mobility. So imagine you are sitting inside a high-speed train, moving at several hundred kilometers per hour. You will still have cellular connectivity. And the last important part is energy efficiency. You are talking about couple of orders of magnitude improvement in network energy efficiency. The second part of the 5G standard is what is called MMTC. You are talking about machine-to-machine communication. So basically something like IoT would be pulled in under the standard. So imagine a scenario where you have a high density of devices. So you're talking about several hundreds of thousands of devices concentrated in a very small area. Each of these may not be using up a lot of data, They may only be turning on periodically and transmitting the data, but the system still needs to support such large density of devices. And the third part is going to be very low latency and very reliable communication. You are talking about cases such as virtual reality and so on. So these are the three major use cases of 5G. And if I were to draw a so-called spider web of the improvement in 5G, so the inner spider web shows the what was in LTE, which was IMT Advanced, and now IMT 2020, which is 5G, would have improvement in almost every aspect. And as you can see, the network energy efficiency is expected to increase by 100x, area traffic, by 100 times, and so on. Now, in the next couple of slides, I want to concentrate on the new part, on the new radio part. So what is new about the radio in 5G? So there are many other aspects that I will not cover here because of paucity of time, but I will cover the ones that are related to the radio, which are going to be 3 of them. The first one is operation in the millimeter wave bands. So normally millimeter wave bands refer to frequencies or the frequencies in the electromagnetic spectrum where the wavelength is of the order of 1 millimeter to 10 millimeters. So you are talking about frequencies between 30 gigahertz and 300 gigahertz. However, this is, you can imagine that even if you operate, slightly less than 30, that would still come under the ambit of millimeter wave. There are several advantages of operating in the millimeter wave band. So the first one is the availability of bandwidth. As you can see, there are huge tracts of bandwidth, especially contiguous bandwidth, that are available. If you go back to LTE, what used to happen was that you had to stitch together small pieces of bandwidth to get the really high data rates of the order of 100 megabits per second. Whereas in 5G, in the millimeter wave band, you will most probably have one single big piece available to a user in cases where they need very high bandwidths for short periods of time. Obviously, this leads to possibility of very high data rates. The other advantage of this is that because you're operating in millimeter wave, you will need to use very high directivity, but the advantage of using very high directivity is very low interference from other users. Now, this has a flip side. The flip side is that the reason you need high directivity is because of high path losses. As you go higher and higher in frequencies, the path loss from the transmitter to the receiver increases quite a bit due to various reasons, including absorption by atmospheric molecules. And therefore, you need to do a combination of techniques. You need to use a combination of techniques to combat this path loss. One of them is what is called beamforming. So basically, you use an antenna array and a bunch of phase shifters to steer the beam electronically towards a particular direction. Now, till a year or two ago, a lot of things related to millimeter wave were not in place to do research easily. For example, if you want to put together, imagine you do not have the capability to build an integrated circuit at these frequencies. You need to put together readily available components, but unfortunately, a lot of these were not available, right? Obviously, proven circuit PCB substrates did not exist. Phase shifters operating at these frequencies were not easy to come by. RF components, amplifiers, low noise amplifiers, power amplifiers, mixers, etc., were also not easy to come by. So that is one aspect of 5G. The second aspect of 5G is what is called massive MIMO. Massive MIMO is going to be used in the frequency range below 6 gigahertz. But the idea is that you can use a very large array of up to 256 antennas to serve multiple users simultaneously. So you would have multiple transmitters and receivers on the base station side, and quite possibly on the cell phone side also, or the user equipment side. And the base station has the ability to talk to multiple cell phones at the same time. This does not exist in today's world. Normally, the base station would have to do time division multiplexing. So each user gets a small chunk of the base station time. And this type of massive MIMO, such a massive MIMO system could very potentially have very, very large data rates also. And you can do beamforming in the base band to get very high directivity. The third piece of technology that is going to come to fruition very soon as part of 5G is the so-called full duplex wireless communication technology. So if you look at today's technologies, wireless technologies, all of them fall under one of these two systems shown on the left. So the antenna, a single antenna, is used to both transmit and receive by splicing it either in the time domain or the frequency domain. In other words, either part of the, or you transmit in one frequency band and receive in another frequency band. If you need to do both transmission and reception at the same time and in the same frequency band, you will find that you hit a big wall in terms of technical issues. The obvious first technical issue is the fact that the transmitted signal is extremely high in power content because of the fact that you need to reach a very, very far away receiver. The signal that you are receiving from the remote transmitter is going to be very small. So to be able to receive the extremely small signal without without saturating your receiver requires you to cancel your own transmitter. So that comes under the ambit of self-interference cancellation. Obviously, you might need to modify the protocol the way you would implement the baseband algorithms and the protocol, right? So you need to figure out whether this is going to be transparent or it requires a modification of the protocol itself. And there are other issues involved here. You may have to redesign parts of the transmitter to achieve, parts of the receiver to achieve even more cancellation if required. But obviously the advantages are really, really large. Without using extra antenna elements, extra space, extra, too much extra circuitry, you instantaneously, theoretically double the available bandwidth. Obviously, if you modify the protocol, if you modify the signal, etc., there are going to be overheads, but the idea is you should be able to get as close as possible to this theoretical doubling factor. Apart from this, it also helps you do things related to channel quality. So in the second half of the talk, in a few minutes, I'm going to come to this full duplex communication and show you one example of a full duplex transceiver. Now, what's so special about specific portion of the 5G standard? Well, it turns out that the Indian scenario is quite different from what was normally considered in the 3GPP standard. For example, our urban population densities are extremely large. Our rural deployment scenarios are extremely different compared to what you would normally imagine in Europe or the USA. The atmosphere, air quality, humidity, etc. are quite different. The temperatures are different. So you might imagine that new channel models need to be developed for India. Finally, the Indian data usage scenario is quite different from what the way Indians use data is quite different from the way an American or a European would use data. So that is the scenario from which the Indian team which attended the 3GPP standards approached this. I'll give you an example specific to the rural scenario because that is an important mandate of the 5G deployment in India. If you look at the 3GPP standard, the model of the rural scenario is as if you have a high-speed vehicle passing through a non-urban area. So imagine you're in a vehicle on a highway between LA and San Francisco or New York and Washington DC. So you are basically traveling in your own car and you need to have high-speed connectivity. But all of us know that the Indian rural scenario is very different. So the Indian 5G team came up with a concept called a low mobility large cell. So the basic idea is that we wanted to develop Indian 5G requirements and solutions that will be specific to what India needs And hopefully this will be done through Indian companies and academia getting CPP standard. Now, what do I mean by this? So, if you look at the the Indian rural internet connectivity, you basically have the optical fiber backhaul going to the gram panchayat, and from there you can have the gram panchayat gets very high speed connectivity. The typical intersite distance is about 6,000 meters, and around the gram panchayat you have several villages. Now, India has about 2.5 lakh gram panchayats and about 6.5 lakh villages. So, as I said, the base station at the gram panchayat should serve the nearby villages. So, what we did was we went ahead and built the list of gram panchayats and villages, looked at the latitude, longitude, associate each village to the closest gram panchayat possible, and found out the distribution of the cell radius versus the connectivity. Right, this plot on the left shows the distribution of the maximum distance of a gram panchayat and its associated villages versus the coverage. And it turns out that if you choose a 6 kilometer radius cell, you would cover 95% of villages. So what that means is you need to move away from what the 3GPP standard states. The 3GPP standard does not give you the size of the cell, but it turns out that the typical size of the cell is going to be quite small. Now, that is where the large cell part comes. And we know that inside each of these cells, the mobility is not at very high speed. So you have the low mobility large cell. And what is going to happen, what has happened is that these enhancements of low mobility large cell have been put into the 3GPP 5G standard. It hinges on a key piece of technology called pi/2 BPSK. It's a specific type of BPSK with a phase rotation. Now, more specifically, the advantage of this is that it exhibits lower envelope variation. So the peak to average power ratio is lower than the typical 5G cellular signal. This improves the power amplifier efficiency at low data rates. So that when pi/2 BPSK is enabled, you can push the power amplifier closer to saturation and therefore operate it at higher efficiency. The advantage is that you get twice the range because you are operating at twice the transmitted power. In terms, the 5G group, academia and industry from India who have attended the 3GPP meetings have ensured that this has been partially accepted into the 3GPP standard. For the sub 6 gigahertz range, it is optional. For the millimeter wave range, it is mandatory. What will happen is that in the Indian case, it will be mandatory for both sub 6 gigahertz and millimeter wave. If you travel internationally, you will find that it's optional on the millimeter wave side. So that kind of covers the first part of the talk, which covers the 5G standard and what is specific about India. In the remaining time, in the next 10 minutes or so, I will present one small piece of the of our research work on full duplex wireless communication. If you look at conventional transceivers, at every antenna, the received signal is extremely small compared to the transmitted signal that you are sending out. And we want, in full duplex systems, we want TX and RX to operate at the same frequency and at the same time. So this element, the duplexer element, is really key to achieve this. What are the common duplexer elements available to us? It turns out that the most common duplexer elements, relatively simple in construction, are the circulator and a transformer. It turns out that circulators are relatively narrow band as far as the phase response is concerned, and they are also bulky, and it's very difficult to integrate them with a mobile transceiver. The isolation is about 20 dB that you can get from a circulator over a narrow band. transformer isolation is higher. You can achieve about 40 dB over a narrow band of frequencies. And it turns out that it is possible to integrate this in CMOS technologies. But again, I will point out that getting 40 dB over a wider band is relatively difficult. Now, our work hinges on a particular class of duplexers called electrical balance duplexers. More specifically, electrical bridge-based duplexers. So the basic idea is that if you take an impedance bridge, it turns out that the null frequency depends on the ratio of impedances, and these elements can be controlled easily to obtain wideband isolation. Now, what we realized early on is that inductors and transformers are always going to be relatively narrowband, and they are going to have low quality factors. What is the element, the bridge element, that can have very high quality factors and possibility of easy reconfigurable nature? You are looking at capacitors, because capacitors in most CMOS technologies have extremely high Qs of the order of 100 to 200 in the gigahertz range. And it is extremely easy to use MOSFETs as switches to control the impedance of the capacitor, to build a capacitor bank. So under the balance condition, you can ensure that the ratio of the capacitors is equal to the ratio of the antenna and the balanced impedance. So this slide shows a block diagram of the receiver, of the self-interference cancelling receiver that we built. It includes the duplexer and the rest of the receiver. So the duplexer consists of a capacitive bridge. So these are C1 and C2. This is the antenna port, and this is the balancing impedance. Now the output comes out as a differential voltage, which can be then converted into single-ended using a balun, and then received using a receiver, conventional receiver. So you have the low noise amplifier here, a passive mixer, a current mode passive mixer, and the transimpedance amplifier with a single pole baseband filter. This is the fabricated integrated circuit. As you can see, the self-interference cancelling circuit does not come cheap with respect to area. The area is almost 40% that of the, almost half the size of the rest of the receiver. The total area is about 0.73 millimeters square. Now, I'll present in the next few slides the measured results on the integrated circuit that was built. As you can see, the mean isolation in a 20 megahertz bandwidth. So, for example, standard Wi-Fi bandwidths are of the order of 20 megahertz, 802.11g. Standard LTE bandwidths are also 20 megahertz without carrier aggregation. You can see such a electrical balance duplexer can achieve a mean isolation of about 55 dB across the 2.4 to 2.6, or almost over 200 megahertz. We can achieve about 55 megahertz mean isolation. If you have a narrower signal, you can achieve even better. As you can see, you can achieve better than 60 dB, or in some cases even better than 70 dB over a much narrower band of frequencies. Now, the other advantage of the capacitive duplexer comes into play in the next couple of slides. You may know that most data networks are of an asymmetric nature, right? It turns out that, for example, the use of your cell phone, you have much higher download requirements compared to the upload requirements. So the data rate in one direction can be larger than the data rate in the other direction, which means you have an asymmetric link. It turns out that you can tune this capacitor band to get better insertion loss and trade off noise figure for insertion loss by changing the capacitor ratio. And this slide shows that the sum of noise figure and insertion loss remains the same, which means that the overall noise figure and insertion loss on the TX side can be tuned and can be traded off. And this shows the IIP3 of the receiver. It's about -4 dBm. With TX cancellation, you can see that this shows extremely high IIP3. The frequency response, gain, noise figure, and insertion loss are extremely flat over the 200 megahertz range. Now, this is a summary of the duplexer. This works. This is the only work that we know of with a tunable RX-TX insertion loss, and it meets the wireless LAN 20 megahertz. You can easily achieve 50 dB of digital cancellation, which seems to be quite common. So I will not go through the last part because we don't have time. I think we are running out of time now. So I will end the talk here and receive any questions that you might have. Thank you.
Oh, thank you very much, Professor Anirudhan, for a very interesting talk. So is there any question from the audience? If you want to understand anything about 5G, this is your chance. Yes. Any questions from the audience? Okay, I don't see any questions. So maybe Professor Anirudhan, you can continue for a few minutes, up to 2 minutes on the test bed also, since we don't have any questions.
Sure. Thank you. I'll do that right now. So I only have 4 or 5 slides on that. Just to give you a quick overview of the 5G testbed project. So this started in 2018 in a very big way, but it was started even before that as part of a large Ministry of Electronics project. So it was first proposed by Professor Paul Raj of Stanford University way back in 2011 or 12. And the present avatar is funded by the Department of Telecommunication. It's an extremely large project. It's a 240 crore project, and it is going to end in the middle of 2021. And we are actually well on our way to completing all the hardware and software requirements of this project to build an end-to-end working system. So the major goals, of the 5G testbed project, there are actually several goals. It's to encourage telecom product startups, develop R&D capability in India, and obviously this has spurred the team to build something that is specific to India. I covered that, which is LMLC. Now, we started way back in 2015 with a Ministry of Electronics project. I have that down here. And that has, the first phase was funded by MIT. The second phase has been funded by the Department of Telecom. Now, of course, there have been several contributions that have come out of this. There are about 120 contributions that have been submitted to 3GPP. LMLC is now going to be part of 3GPP, and it is going to be part of the Indian deployment of 5G technology. There are 8 organizations that are involved here. IIT Bombay, IIT Hyderabad, IIT Madras, IIT Delhi, Indian Institute of Science, CIVIT, which is Center for Excellence in Wireless Technology, which is located in the Research Park. SAMIR, which is a Ministry of Electronics organization that concentrates on antennas and electromagnetics, and of course IIT Kanpur. So there are 8 organizations that are part of this testbed. The final, once we finish next year, there are going to be 5 test beds located at 5 different places: IIT Delhi, IIT Bombay, IIT Hyderabad, IISc, and IIT Madras. Now, each of these test beds will be unique in a certain way, right? So, for example, IISc is doing Li-Fi, IIT Madras is doing millimeter wave, and so on. So each of these will have its own, version of the test bed. The idea is that if anybody builds something that is amenable to the 5G standard, but does not have the rest of the ecosystem to test it, they can go over to any one of these test beds, to the appropriate test bed, and test. It could be a startup company, it could be an university. They can go and test it at the appropriate test bed. That is the basic idea of having different types of test beds. So I think that's all I have here. Just wanted to end by noting that there are currently more than 200 researchers, project associates, senior project officers, and professors working on this test bed, making it a reality.
Okay, thank you. Just one question I noticed. I think it was from a devices people. This technology is really booming, and there is another technology in the devices area, which is the gallium nitride technology. That is also a lot of things are happening there. So someone asked the question: is there a confluence of the two? Does gallium nitride technology have any role in this?
Yes, there is indeed. So what we are so as part of building the hardware, if you see here at IIT Madras, for example, we are building hardware platforms related to both the sub 6 gigahertz as well as the millimeter wave portions of the 5G standard. And indeed, we are trying to build power amplifiers based on both LDMOS and gallium nitride. And gallium nitride is deploy this in a very big way, because the power requirements are actually extremely high for 5G. So, for example, the peak power requirements is of the order of, if I remember right, several hundred watts of modulated beam power. So, the requirement of highly efficient power amplifiers, which of course at these power levels means gallium nitride power amplifiers, is a very important requirement.
Thank you, Dr. Aniruddha. Yes, certainly. I guess this is in a huge topic, so we can certainly go into details of many other things. So, but I think we should conclude this talk here. So we will thank the speaker. Thank you very much, Dr. Aniruddha. I'm sure we will have ample scope to hear about all these fascinating systems in future, again, in more depth. Thank you very much.
Thank you.
So we will now move ahead to the next talk. So please remove these slides so that the next speaker can share his slides. Thank you very much. Okay, so our next speaker is Dr. Venkat Vanukuru. He is from the well-known company Global Foundries. Okay? So Global Foundries, as you know, it works on devices, okay? Fabrication of devices on chip. And Dr. Vanukuru in particular is an expert in the area of design and modeling of passive on-chip components. So he has his PhD degree from IIT Madras, and for the last 12 years he has been with Global Foundries, and he has a lot of experience in passive components on chip. So some of these things he is going to share with us today. As you can see, his talk is entitled Designing and Modeling of Silicon Passive Devices. So Venkat, over to you. Please carry on.
Okay. So Dr. Ananjan, can you?
Sorry, your sound is cracking up. No, I think there is something not okay with the sound. Can all the other speakers, please, other attendees, please turn off your mics? I'll also turn off my mic.
So is it any better now?
Yes, Venkat. Yes, it's better now. Definitely.
Okay, great. Thank you. So, good afternoon, everyone. Myself, Venkat from Global Foundries. I'm a part of the technology enablement team. And today, modeling of passive devices, mostly for in silicon technologies. So the outline of the talk is like in 5 minutes, and then we'll touch upon a couple of important inductor and transformer configurations, especially for silicon, and then we'll and then conclude the talk. Okay, so if you look at what we have in a cell phone today, so we have a bunch of antennas, and then we have the baseband stuff, and then followed with the digital. So most of the presentation, which is the first block that is there right after the antennas, and some of the devices that we see in these low noise amplifiers, power amplifiers for transmit, and then VCOs. So most of the okay, and then when we talk about these front-end modules, so these are mostly RF integrated circuits. And like analog circuits, we care about something called matching to minimize the reflections, and then to critical for the operation of these circuits. So one of the other things that needs to be understood is, it's just not. It's also possible to have silicon-based passives, which are extremely smaller in area, but then they come with temperature dependence, bias dependence, and die-to-die variation, all of that. So precision passives. So over here, what we are looking at is some of the production level parts of the Apple a VCO. So the only thing probably we can make out with our naked eye are these inductors and transformers, which are. So now it turns out that these passives account for more than 60% of and also the performance. So with that motivation, let's get into one of the circuit blocks, which is an LNA. Inductor for the input match, the source inductor again for the input match, and the drain inductor for the output match. The parallel resistance of the inductor is the series resistance times the Q square. So every time we have a higher Q, we have a higher. Now what it means for this circuit is, let's say if we have just not a cascode, this is a cascode LNA by the way, but inductor comes with a parallel resistance, and then that sort of dampens the gain. So higher that we see here provides a DC drop, which is going to provide negative feedback. So high Q for
Venkat, sorry to break in. Your sound is distorted. Every few seconds it kind of breaks up. Are you using a separate speaker and mic?
Yeah, this is an integrated mic from the. Sorry about this. So
maybe you can check your sound settings or some setting. It's every few seconds your audio gets garbled.
Venkat, it may be a bandwidth issue. Pausing your video and seeing if that helps too.
Okay, I have a very high speed internet.
Okay, go ahead and let's see.
Can you hear me okay, Dr. Ananjan?
Yes, now things are better. I think the problem is resolved, I think, at the moment. Please go ahead and let's see.
Okay. Yeah, just let me know if you still see any issues with the voice quality. Then I'll probably turn off my. Okay. So, and then the most important piece over here is the gate inductor, because the signal has not gone through any gain stage, and the resistance associated with the gate inductor just adds directly to the overall noise figure of the receiver. So, what this chart is trying to tell us is that high Q inductors and essentially all the passives is extremely critical for all the front-end modules. So in this case, gain and noise figure of the LNA. In the case of a power amplifier, it is the efficiency of the amplifier, and then in the case of a bandpass filter, the insertion loss. In the case of a VCO, the phase noise. Whatever the performance metric of the RF circuit is, in one way or the other, the passives directly impact these performance metrics. So now let's get into the device itself. If we look at the inductors, traditionally they're made as spirals. So what we do essentially here is to spiral in on one of the top metals with very less resistance, and then come down using a via, and then come out through an underpass at a different metal level. So this is the structure. The reason why we have the spiral inductors, because we get increased inductance density because of. And then if you look at the cross-sectional view, and then try to build an equivalent circuit model for these inductors. So you have the self-inductance and the mutual inductance, everything put together as LS, this is spiral inductance. And then there is resistance associated with the spiral, which is coming because of the DC resistance. And then the resistance increases with frequency due to skin and proximity effects. And then you have a self-capacitance, which is because of the distributed capacitance across the segments of the spiral. Okay, so this is how the inductor model would look like for an air core inductor, let us say. But now that we have this inductor on silicon, we have coupling to the substrate, which can be modeled using two distributed lumped capacitors, COX1 and COX2 over here. And then the parallel RC network models the dielectric nature of the lossy silicon substrate. Okay, so this is the equivalent circuit model, and this is the cross-sectional view, and this is the top view of spiral inductors, which are realized on silicon. So now, what is the inductance that we can get per unit area, and how much energy we can store in this inductor in the form of magnetic field, until what frequency we can use this as an inductor, and for differential circuit symmetry. And so these are some of the performance metrics of on-chip inductors. And if we look at the Q characteristics of these inductors, so initially they start increasing with frequency because of Q is equal to omega L over R equation. So as frequency increases, there is resistance to this increase because of the denominator R, which also increases because of skin and proximity. Then we hit the peak because of the bottom network capacitances. So what happens essentially is when we're trying to pump RF current into the inductor, so these capacitors start shunting down that current. Charging these capacitors, which is not going to help the Q, because we're talking about the magnetic energy stored in the device. So then we start going down, because every time we increase the frequency, we are only charging these distributed caps and not the inductor. And then eventually there comes a frequency where no current is flowing through the inductor, and the device starts behaving like a capacitor. So these are the Q characteristics of typical on-chip spiral inductors. Okay, so now if we want to improve the performance knobs, so one of the things is the thickness of the spiral. Essentially, we can build thick metals in today modern RF CMOS processes, or we can sandwich 2 or 3 metal layers to get higher Qs or to get lower resistances. So you could see that that all works, all that physics works in lower frequencies, several megahertz. But then when we get to the gigahertz frequency range, because of the skin and proximity effects, you see that increasing the thickness is actually not helping the Q big time. Okay, so to 2 to 4, yes, there is some increase in the Q, but beyond 4, even if you go to 12 micron thickness, it's not much we are seeing in the inductor Q improvement. And then high resistivity SOI processes, SOI technologies, even GaN technologies, other technologies where the handle wafer is high resistive is always known to have higher Q characteristics. And it is because of this, essentially, if we have a high resistivity substrate governed by the dielectric relaxation frequency, even at lower frequencies, the substrate acts predominantly as a capacitor. So if the series cap of these two, which is essentially much lower than the distributed oxide cap. So what happens is every time we increase the substrate resistivity, both the PQ value and the PQ frequency of the inductor starts increasing. You could see here. But then beyond a point, let's say 10,000 ohm centimeter, there is no further increase in the PQ value. So even this technique, process technique, shows limit for performance improvement. So then the next thing that we could do is to optimize the spiral structures itself. And this is a very famous work that was done back in 2000. And so what they've done here is to reduce the spiral losses by optimizing the width. And so here the idea is to find out where the ohmic losses are dominant, and because of the longer channel, longer lengths, the outer turns have much more ohmic losses, and due to higher magnetic fields, which the center of the spiral, the magnetic losses are dominant. So the idea is to essentially have wider to reduce the ohmic losses and narrow inner turns to reduce the magnetic losses. So that's what we call as tapered inductor. Or so these are this is a standard inductor and this is a tapered inductor. And taper is the amount of the change increases as we move from outer turns to inner turns. So you could see that taper 0, you have a much higher DCQ to start with, but then as you go to the operating frequency, in this case, let's say a 5 gig LNA, at the operating frequency, the Q drops down dramatically because of the proximity effect. The proximity effect is the current crowding effect because of the magnetic field set up by all these currents flowing through the. As we start increasing taper from 0 to 1, 1 to 2, 3 to 4, so you would see that the DCQs are dropping because you are cutting some portion of the metal that is going to affect the DC current or the area that is available for the losses are getting minimized in the inner turns. So you would see that the proximity effect is reduced and the Qs at the operating frequency are shooting up. Okay, so here you see that the Q has gone up from 15 to 25 almost at the operating frequency just by 0 to 4. So it's a trade-off that normally we can do by sacrificing the Q at DC. We are getting Q at the operating frequency. So obviously this is a good idea for something like a gate inductor for an LNA. But then when we talk about power amplifiers, this may not be a good idea because it's going to hurt us both in electromigration and also the DCQ. Okay. So this is a case study where we want to get 8 nanohenry inductance for a 2.5 gig LNA. So these are various combinations that can give us the same 8 nanohenry inductance at target frequency. So narrower turns have higher self-inductance. If you want to get the same inductance, we have to increase the number of turns so that though we lost on the self-inductance, we got the mutual inductance. So essentially all these combinations would give us 8 nanohenry inductance. So here, and no magnetic losses at all, whereas over here the outer turns are wider, so not really ohmic losses but magnetic losses. So if we look at the Q characteristics, so as we increase the width of the spiral, the Q starts increasing, and because now we are reducing the ohmic losses, but then after this the magnetic losses are becoming dominant, and then the Q starts dropping. So this is the optimum width for the desired inductor. Okay, so they'll find out what is the optimum width and turns ratio combination to get the highest Q possible. So what these tapered inductors are doing is that they are pushing the, because we are not having the magnetic losses anymore. So you could see that the optimum width, the optimum number of turns combination is different, and also the PQ value is quite different. Okay, so because as you increase the width and number of turns, you are increasing the area of the spiral. So that essentially means that you are increasing the distributed capacitance to the substrate. So this idea of inductors can be extended to stacked transformers as well with tapered spirals. So where you have the transformer primary on the top metal and the transformer secondary on the bottom metal. And so what in Q and 15% reduction in insertion loss without any change in other characteristics. Okay, so this is one class of inductors where we are trying to minimize the resistance and improving the Q. So there are other class of inductors which are symmetric inductors where the Qs are primarily limited by the capacitance within the spiral. And if you look at what happens in these symmetric inductors, which are used in differential circuits, so there is huge adjacent turns of the spiral, because the ports are seeing plus delta V and minus. So if it is single-ended inductors, so if this is V, this is 0. So the neighboring segments of the spiral do not see very high voltage gradient, but and differential signaling, the adjacent turns of the inductor see a very high voltage gradient. Okay, so what that means is associated within the inductor, and then that pulls the Qs down. Okay, so for example, let's say we want to get something like 70 nanohenry inductance for Qmax has Qmax and SRF values like this over here. Okay, so the Q is only 5 or 6. Okay, the inductance is about 70 nanohenry. Now what we can do is to minimize this lateral capacitance, we can have an alternate layer symmetric inductor where turns are, let's say, realized on the top metal, and all the even turns are realized on the bottom. Return capacitance is reduced, and then you could see there is some reduction in the mutual inductance as well. So the inductance drop slightly, but then there is a PQ frequency and self-resonant frequency. Okay, so you could see that the Q increased from 5 to 8. Okay, which is a significant increase. And then is to have two series inductors connected back to back, which can meet the target specification of very high inductance and still have structural symmetry. Okay, so these are two symmetric series inductors. And what happens in series inductors is that the voltage distribution follows something like this. So we spiral in from V0 and then from V0 by 4 we come to the virtual ground, which is 0. And the opposite happens in the other phase, and -24 and 0. And this is the equivalent circuit model. So you have a huge capacitance between the top and the bottom layer. The capacitance, lateral capacitance has come down, that is agreed, but the vertical capacitance across the layers has now shot up, okay? And a significant boost in the Q. So you could see that, the Q further in the self-resonant frequency is also pushed up. And if we were to look at the distribution of capacitances within this network, so the total capacitance is down and not the metal to substrate capacitance. So we could do further better, which is a solenoidal series pair inductor, where we do one spiral, drop down, do two spirals, and then come up, do two spirals, drop down, and then continue the spiral. Winding connected back to back to realize the symmetric inductor. So if you look at the voltage profile, so the both the lateral capacitance and the lateral turn-to-turn capacitance and the vertical layer-to-layer capacitance, both are minimized in this structure. And you could see that the Qs are further pushed to 12. So we started from 5 and we just pushed the Qs all the way up to in the structure. So these are some of the things that we can do in the design of these spiral inductors for improved performance. So these are some of the performance numbers, how these things compare with prior art. And the same inductor can now be used in a transformer where we wrap around big around them, and then this becomes a very high turns ratio transformer. So you could see that the turns ratio is about 9, and so the bandwidth is also quite good. So Shankar and Anirudhan pointed out, millimeter wave applications are heating up. So we have several devices that are several devices being used for building these circuits, and some of the important ones again are inductors, capacitors, and transformers. So like we discussed in the initial charts, at higher frequencies, it is the capacitance within the structure which is going to limit the overall Q and resonance. So what we have suggested here is conical inductors, which essentially have very low capacitance across the turns and also across the close to 20% improvement in Q is possible just by adopting this conical inductor approach, certain frequencies to higher values. So another interesting thing that happens in millimeter wave is the Q of the capacitors. So usually if you look at the resonators, the Q of the inductors dictate the overall Q of the tank circuits. Because if you look at sub 10 gigahertz applications, the inductor Qs are pretty poor because of skin and proximity effect losses, all the physics that we talked about. So inductor Q is about 20 and the MIM Q is about 300, 400. So, all the time when we discuss sub 10 gigahertz, it is the Q of. But then when we go to millimeter wave, the Q of the capacitor starts dropping with frequency, whereas the inductor Q goes up. So it so happens that, let's say if you're looking at some 60 gigahertz application, the inductor Q could be easily 30, whereas the MIM Q is also close to 30 or 40. So now both of them have an equal say on the resonator Q. So instead of having these MIM capacitors, we can use interdigital MOM capacitors. So here the dielectric is just the silicon dioxide 4.1, But then the best part is that the loss tangent is much lower with the SiO2. So we take a hit on the density, but then because the absolute value of the capacitance that is required at these frequencies is so small, the penalty we pay on the area is not really so critical when we look at it in the context of an entire circuit. Okay, so what we see here is simulation results of so with higher dielectric losses at millimeter wave, MemCap suffers lower Q, whereas the MomCap has very, very high Q, above 400. Okay, so and then the transformers, transformers are more heavily used at millimeter wave than the inductors, because the amount of power that we can get at these frequencies is so small. Invariably, we use some kind of a transformer power combining at the output for power amplifiers. And then there are a whole bunch of other things that these transformers can help us, like single emitter differential and vice versa, balance, so on and so forth. So if you look at these transformers, there are two different ways in which we can do them: planar transformers versus stacked transformers. Then pretty much the planar transformer is what we are talking about. But most of the modern RF CMOS processes, they have two thick metals, especially for transformers. And in such a situation, it is always better to have broadside coupled stacked transformers like what we see over here. Inductance and Q characteristics. So you see that for the planar transformers, there is a significant difference between primary and secondary inductance. Whereas if you look at the stacked transformers, the inductances are very much the same, and so are the Q characteristics. So both from a symmetry standpoint and a Q standpoint, they have much better performance than transformers, and they have much higher coupling coefficient because of their length and area, and then also efficiency, to 10% higher. So these are used for millimeter wave. Okay, so I think we'll conclude the presentation. So what we've seen is precision passives are supercritical in all the RF front-end modules, and they're heavily used, unlike digital and analog circuits. So these devices are challenged by the Q that can be achieved. And we've looked at some process routes. Both of them have limits, and then they hit their saturation values. Not much can be done with the process. So there are innovative structures that can be looked into for improvement. So the problem with these structures is we may not have foundry supported compact models. We may have to use EM tools to optimize these devices. But then when performance is at stake, we can go ahead and do that. And there's plenty of scope for research in this domain. And we've looked at two different inductor configurations. One where we reduced the proximity effect losses and the resistance of the spiral, boosted the capacitance within the structure, and increased the Q of the spiral and the self-resonant frequency. And then we have briefly touched upon some of the millimeter wave passive devices that are used in circuits. Okay, thanks for your attention. If there are any questions, I'll be glad to take them on.
Okay, thank you very much, Venkat, for your presentation. Any questions from the audience? Any questions?
Was my audio okay, Dr. Ananjan?
It was okay. It was still a little distorted, but we could manage. Yeah. Okay. Any questions on this? Anyone wants to know something detailed about on-chip inductors and these things? Okay. I had just one question, Venkat. We have periodically we hear about this concept of high Q active inductors and active Q enhancement. Uh, is there anything practically useful done in that area?
I mean, it is good for research, but when it comes to product level parts, the variability associated with that inductor is so high, really useful for narrowband circuits. And so most of the ICs that systems are narrowband. So yeah.
Okay, so if there are no further questions, then we will conclude this talk here. And thank you very much, Venkat, for sharing your knowledge. Thank you very much. And we will move to the next talk. So, Venkat, please. Okay, so we next have talk. The presentation. Soumya Ranjan Panda is at the speaker, I think.
Yes, sir.
Yes. So this is a regular contributor talk. So Soumya Ranjan, please go ahead with your presentation. Share your screen.
So now I am like both audible and my screen is visible.
Yes, it's fine. Please go ahead.
Yes, thank you. So today I will be presenting on silicon germanium heterojunction bipolar transistor device characterization up to 500 gigahertz. So, and also I will be discussing a bit about like what are the uncertainties that creates the problem. So I am Somiranjan Panda. Will be presenting, and this is funded by different organizations. So first I will discuss like what is the need of proper characterization, accurate characterization, then the measurement procedure that is followed in this course, and then the results, then uncertainty and conclusion. So if you'll see like the first step always like okay, suppose we want a system design, we want suppose a low noise amplifier for any like system RF system. Then at the the first stage is the device fabrication. So once we have the device, the next stage is always the characterization. The characterization is important. It is because now once we have the characterization results, we need a compact model. We develop a compact model based on the results, and from the compact model we design the circuit or system. So if your characterization is wrong, then sorry, if the characterization is wrong, then the compact model will be wrong and then the system will be wrong. So that's why the characterization part is important. Even once we have the characterization, now we have the compact model and we designed a circuit, but it is not meeting our specification, and again we need to go back to the device fabrication and go back for the characterization. So that's why characterization is quite important for a system design. Now, if you'll see that what does mean that accurate characterization, like when we are talking about accurate characterization, what it means is, so always like we'll have the device that is inside, then we'll have some backend of lines, different metal layers, bias and all. Then we'll have some RF pads, etc. to measure or to characterize the device, and it will be connected to the through the LNA, through the VNA to the system. So now the accurate characteristic means we need the characteristics of this device, not all these things. These things needs to be removed properly so that we can exactly know the exact characteristics of this device. So in this case, like to up to like characterize up to 500 gigahertz, the four systems that are used. One is for 1 to 110 gigahertz, the another is 140 to 220 gigahertz, 220 to 325 gigahertz, and 325 to 500 gigahertz, using different extenders. For 1 to 110, the extender is use this one N526060003, And for the other three, there are like this ZC220, ZC330, and ZC500 extenders are used. So this is the extenders, and here we put the RF like wafer, and here the probes, and it goes to the VNA. So now if you'll see there, so how we remove this like parasitics or other things that are not required, because at the end that we discussed, like, okay, we need the device characteristics. So what it does is that two things. One is calibration and de-embedding. So what does mean the calibration? Means what we'll do now, there are two type of calibration actually. So what are the two types of calibration? There will be always a known like set of like components, or we can say duty device under test. So what we do is we always characterize those. So once we have those results, then we characterize the whole device including this back end of line, etc., and then we subtract this known parts. This ISS means impedance standard substrates. So we subtract those parts. So whatever we get is the like we can say device characteristic. Of course, there is another stage that is the de-embedding, that I'll talk a better way. So now what it means is that there are two things: off wafer calibration and on wafer calibration. Off wafer calibration means, okay, we have a wafer and we have the device in that one. So in case of off wafer, the calibration kits are different. Those are basically standard calibration kits supplied from different brands. Like in this case it is from Cascade. So we have some known standards, but those are not on the wafer that we are characterizing. So these are some others. So that's why that is the off wafer. Off wafer doesn't mean like it is something different. Off on wafer and off wafer, only difference is that in case of on wafer, the calibration standards are also from the same wafer. So now that, then once we have the calibration, so what we does in the calibration, now we have like it is connected to VNA and all. So we remove all the stops, like all the errors from the VNA, etc., etc., and we reach at the probe tip. So in case of off wafer, we reach at the probe tip. Like, okay, whatever we are now measuring, the result will be from the probe tip down to the device. But the thing is, so once we have that, we need to again remove all these backend lines to reach at the device. So those parts are so that is the step that is called de-embedding. So de-embedding means shifting the reference plane. So we reached, so in the off wafer calibration, we reached at the probe tip for the timing, and once we do the de-embedding, so then we reach at the device terminals. But the problem in case of off wafer calibration is that, as I said, that the calibration kits are from different environment. So once it is a different environment, the results are actually not accurate, because when we go higher and higher frequency, we need to have the same like calibration standard on the same wafer. So for that, so that what I was talking about, this different errors when we are reaching up to the probe tip, those are systematic, random, and drift errors. These random and drift errors can be ignored, but the system because these are less, and the systematic error, that adds a lot of error to actually the accurate measurement. So these things are actually we removed in the method of calibration, and then in the method of de-embedding, we remove the information that is down to the device from the reference plane that we reached after calibration. So as I shared, that in case of off wafer, the problem is that the standards are different environment. So we are not sure about the results, and the errors are a bit more. So what we do in on wafer calibration is that in case of on wafer calibration, the calibration standards are also on the same wafer. So once we remove those parts, so like we are more sure about our results, and also in this case we reach almost up to the like metal one stage after calibration. So once after that, we do a subsequent de-embedding, and we reach at the device terminals, and whatever results we are getting, that is the device results. Now let's see the device results. So what we got is this magnitude of S21 we plotted with respect to frequency, and similarly for magnitude of other like S11, S12 page, all these plots are measured. So now whatever the results or characteristics with respect to different bias at VCB, that is collector base voltage 0, that means both VC and VB are varied synchronously. So the results that we can see here. So the results that we measured, that this is the device we are seeing. So there are some issues. What you can see, there are issues here, and we can see there are issues here. These are not accurate things. So what we did is, what we are seeing is the discontinuities above, you can see above 110 gigahertz, the discontinuities, and also if you'll see above 400 gigahertz, there are like peaks coming on. So what are the like reasons that we can see, like in case of this particular set measurements, what we did, what we observed is that the calibration standards that are done are quite close each other, a bit close each other, so that adds crosstalk. So that crosstalk introduces these errors mostly. And also if you see that we have different probes. So for different band, actually, for as I discussed, there are 4 bands. For different bands also we have different probes, so each probe has different like dimensions, so that also introduces some errors. And also the angle at which we are putting the probes, that also introduces some errors. So these are the some of the errors. So we can even better visualize these errors. So for that also we plotted ft and fmax. You can see there are some errors here, and particularly this error is because when we are shifting from one band to another band, the contact resistance the probe makes a little difference, and that gives us different collector current. So that finally gives us a different ft. So you can see it here also in fmax characteristics when plotted against frequency. So you can see that there is a dip at around 50 gigahertz. So that is particularly we observed that it's maybe because of the uh, because if you see that fmax and s12, these are quite related. So in the s12 we observed that okay, there is a dip in the s12 around this frequency, for which we are observing that dip in the fmax actually. So these are the some of the regions that I will be discussing also, that what maybe the regions uncertainties. So for that also, like to observe the exact things, what we did is we made a similar device in tcad. We calibrated it properly. So in this case the calibration is not the calibration we discussed, this is the simulation calibration. That means we are comparing, or we are tuning some of the parameters, so to match the figure of merits, basic figure of merits of the device, so that we can compare our results with the measurement. So for that we measure the cold capacitance, and we compare the junction capacitances, so that we can check about the dopings. And then we compare the Gommel plot, that is the ICIV versus VBE, and we got a good match. Okay, I am not showing the doping profile here, but doping profile are quite compared. So then we compare the FT max. So now we have all the figure of merits compared. So now these are the ideal characteristics that we are getting. So this is the simulated device. So now let's compare both. So when you're comparing both now, so this is what we measured, that is in the symbols, and this is what we got from the simulations. Now here when we are comparing, so now you can clearly see that these errors here, these errors in the band changes in the S12 that I was talking about when we are discussing about Fmax. So all these errors are clearly visible. So but as per theory it should be same, no? But the problem is it is not exactly following. So these errors are still needs to be improved in the characterization, and also it needs to be clearly understood that what are the reasons of these errors maybe. We have also worked on some other process that I'm not talking in this one. So those uncertainties I'm going to discuss a bit more. Although in case the results that I am showing for that particular lot, that wafers were the devices were a bit far west, but still the crosstalk has not been properly removed. And the other reasons of the like errors can be, okay, if you'll see that I was talking about that different calibration standards. So there is a two calibration. Suppose this is a TRL calibration, so through, reflect and line. So the through is like, in case of through and line, if you'll observe, there are two different distances. So when we are putting it or when we are probing it, we need to shift one probe. So when we are shifting the probe also, it creates an error. So probe positioning creates errors. Now when you're putting the, when you're placing the contact also, there may be some surface dust, etc., etc., that also can create errors at this, at such high frequencies. And also as I discussed that we are using different probes for different bands, So the different probes has different dimensions. So each dimensions have different coupling at these high frequencies. So that can also introduce some errors that I'm going to discuss here about actually. So now you can see that 140 to 220 gigahertz this probe is used, and 220 to 325 this is another probe. So these both have different dimensions. So when simulated, that we observed that the electric field profile in electromagnetic simulation is different. That is what makes these errors. So if you are measuring the device, suppose a transistor open DUT, so when you're measuring the intrinsic, when you're simulating the intrinsic one, that means we are without considering the like back end of line and these probe tips, etc., etc. It is quite straightforward. And when we are including all these things, we can see that this is the profile that we are getting, and there is a large discontinuity during the band change from the 220 to 220 when we are changing the probe. So that what introduces the error that I was showing in the figure results. There another thing you will see. Okay, so it is not running. So another thing is, okay, when we are not considering the neighboring devices, if we'll compare the magnitude of S21 with EM simulation, that what is happening is there are this discontinuities that is not observed. That is quite straightforward. But when you are considering these neighbors, actually this is a video I want to play, but I don't know why I can't play it. So when you're considering these neighborhood devices while characterizing this one, so in the EM simulation, what you observe is that gives us the same path we followed in the measurement. So that means these neighbors are also impacting in this particular case. And so these are some of the uncertainties in the characteristics that can be corrected. So now I can come for a summary that okay, we discussed like what is the need of accurate characterization. Then the advantage of one wafer calibration that we discussed, it is because at such high frequency the environment for the calibration should be same as the environment for the device we are measuring. And the various non-idealities that we discuss is different probe dimensions that can be improved, the angle at which we are putting, and the cleanness of the pads, and also this through and line, these movements, all these things affect the characterization for such high frequencies. And so what can be done is that okay, when we are making these calibration standards for device characterization or for calibration, so those needs to be properly checked. And at that point what it happens is like okay, we should said okay, we need to more space and all these things, but it also adds cost. So all this we have to look at the cost, at the same time we have to look at the proper characterization. So there is a like we can say okay, there is a we have to compromise what we can do, and so that at the end we can get accurate characterization that will help the compact model and the circuit design. Thank you. So these are some of the references and publications. Thank you.
Okay, thank you very much, Soumya. Are there any questions from the audience? Those who may be interested in high frequency probing.
Yeah.
Do you have any questions? Please go ahead.
So this was I was showing like the effect of like neighbors.
Okay, so thank you very much, Soumya, and nice talk. So Sunil, I think there are no presentations, so I think we can close the session now.
Yes, yeah. So thank you, Soumya, again for participating and giving a nice talk. So I think, yeah, this part of the session we can now close and come back at 2 o'clock. The first talk at 2 o'clock
Yes.
in the second part of the session. So in fact, I was just writing to Vikas and Sandeep that please send a reminder to the participants who were there yesterday also that the talk in the sessions will start at 2 o'clock.
Sure, sir. We will write. We will write to them.
Yeah, so we are done for this part, I think.
Okay, so thank you. We'll meet again at 2 o'clock.
Yeah, perfect. Okay, thank you.
Okay, thank you.
हेलो संदीप। संदीप संदीप
हाँ।
किस टाइप का मेल लिखना पड़ेगा बेसिकली? कौन कौन
यार,
रहते हैं?
5 लोग उनको रिमाइंडर भेज।
5 लोग कौन कौन है?
उपाध्याय, एरिक,
हाँ। ओके।
या याहियो यांग, मतलब जो रंजन है,
हाँ हाँ
यांग यांग, और
हाँ
प्रभु
हाँ।
सर और राजीव किनी।
मतलब कि सारे टेराहर्ट्ज वाले रहते हैं ना?
5 लोगों को भेज दो। वो मेल है ना, 5 लोगों को रिमाइंडर लिख के भेज दो इसको। जस्ट रिमाइंडर
प्रभु हो गया,
फॉर।
रंजन हो गया, प्रभु रंजन और
हाँ,
प्रशांत उपाध्याय और और कौन रह गया?
रंजन,
प्रभु रंजन,
राजीव,
प्रशांत उपाध्याय, एरिक एरिक फ्रेज और कौन रह गया?
राजीव किनी,
लास्ट वाला बताइयो। हाँ,
राजीव की।
राजीव की नहीं, ये ओरल प्रेजेंटर है।
नो, टॉक है,
ये
इनवाइटेड
भी ये
टॉक।
भी इनवाइटेड लेक्चर है। ठीक है,
हाँ,
मैं 5 को भेज दे रहा हूँ और सीसी कर दे रहा हूँ सबको। ठीक है, अभी तुरंत।
ठीक है,
ओके।
ठीक है।
ओके।
whole thing will settle down soon because all the students are really now irritated and tired. So earlier they were happy that they had got a chance to visit their families, but now after staying almost 7 8 months, they are all tired now. They are coming back to.
Hello, sir. This is Vikas. Here is Vikas. Can you,
Hello, Vikas.
previous time we have not able to just check your screen sharing. So can we
Yeah,
do it now?
yeah, sure. Can we do it?
Let us
Yeah,
check.
sure.
Yes, sir. Yes, sir. Yes, sir. Yes.
Okay. Let me share my screen.
Yes, sir. Fine, sir. We will just check. Yeah.
Okay.
The session will actually start basically at 2 p.m. But
Okay.
yeah, sir, it is visible. It is visible. It is clearly
Visible,
visible.
right?
Yes, sir.
Okay.
So let us wait for I think 20 minutes and then we will come back. Yes, sir.
Okay. Can I just see if the things are running okay?
Okay, sir. Just uh, the yes, sir. It is changing. The slide is changing basically.
Okay.
It is visible and the it is not lagging basically, so it is fine.
One more thing.
Yes, sir.
On the right up
Mhm.
corner, I see all the. There is a menu. Can I minimize it? Is there a way to minimize it?
You are wanting to minimize this share screening.
Yeah, you see that. On the right side, I'll see all the participants.
Yes, sir. Yes, sir. You can just close it. You can just close it on the right side. Yes, sir.
Okay,
you are seeing the participants. Then you just close this tab, the participants tab. There is a cross mark on the right side. I think so. If I am correct, in my screen it is coming like participant screen is there right side tab
Yeah.
basically, and there is cross mark also on the right side, top right side.
I don't have that. I can only minimize it.
Okay, sir. You are in screen sharing mode now basically, so there will be. It is also coming in screen sharing mode participants.
Yeah.
Oh, it should not come basically, but if it is coming, then you have to come back and then close the participant screen, and then
Okay.
you just again share the slide. Then we will check if it is
Okay.
happening or not. Yes, sir.
Okay, so let me check that.
Yes, sir.
1 minute.
You just unshare your screen and then you have to close like participants tab, and then now you
Okay.
can close the participants tab now if it is present there.
Yeah, I don't see that now. I think, but I'm sharing.
But whenever you are sharing, you are getting the participants tab.
Yes.
Let us check once again. So this is also out of my that particular control. But let us check if it is again happening. Then we will see what we can do.
Okay. Now I'm sharing.
Again, you are getting the participants tab.
It's a tab at the. I can move this around.
Okay. So you
still
just
there.
make it in the corner if you can.
Yeah, I am
If it
making
is
it in the corner. But
if you are comfortable, then it is fine. But if you are not comfortable, then we have to ask somebody. Like I am not
Yeah.
also in good control of this WebEx.
Okay.
So
Okay.
yes.
I understand.
So
If you can get some help on this, I think then it would be nice. Otherwise, I'll try
okay,
to
sir.
minimize and keep it at the right lower corner.
Let me share my screen, and then I just check the all the options present there. Let me do
Okay,
that
fine,
so
fine,
that
fine.
I can also see what is happening. So I am sharing my just one screen like this WebEx screen only. It will take time, 1 to 3 seconds. Yeah. Okay, so now my screen is visible like IITD OSA page is opened in
Right.
Facebook.
Yep.
So basically, I am also getting participant screen. Yeah, basically, definitely. So I think there will be some way to minimize it also. Let me check me. Show active speaker video. Okay. Show active. Okay, participants. Sir, what you have to do basically, I think it should be closed. Let me do it. Yes, sir. You just there is a down arrow basically down angle type. You just make it this type.
Minimize.
You just click it. You just click it, and it will get minimized. One
Minimize.
speaker
That's
will
what
be
I could do it. Yeah, I could do it. I could keep it at the lower bottom corner of it.
upper bottom corner, sir. Basically, upper bottom corner there is this edge shape basically angle type structure.
Yeah, I know, but so we
What the
can't
greater
minimize.
than.
We can.
Mhm.
Right. I understand. We can't make it disappear completely, right?
We
That's what you're
cannot
saying.
make it disappear completely. It seems so, but let me try. If I can do something more options, mute all options, manage panels, copy meeting info view, switch video camera, change virtual background, health checker, polling. No, this is not assign. Not these are for the videos. Chat, annotate. I think, sir, this will remain. This will remain. You just
Oh, is
make
it?
it in the
Okay.
corner, and
Hmm.
this should it cannot be removed. I think so also.
Can you maximize your screen? In the PPT mode. Let's see how that looks like.
Okay, sir. Okay, sir.
For
Okay, sir.
me,
Fine.
for example, how does it look like? I can visualize what my screen would look like for the other participants.
Okay, sir. So I am presenting one of my PPT. Let me do that. I have to open the Microsoft PowerPoint. So let me do one PowerPoint. I see double E poster I am opening. My poster was there. So I am just opening that poster. It will take 1 minute. 1 minute, 30 seconds, basically. Only 30 seconds. I think so. So this is my PPT and I am sharing it now. So it is looking like this, sir.
Okay, fine.
So it will be large, but what will happen now if some participants are seeing it via not making it large view and not making it like basically expanding it. So they will see the screen, but they will see the text will be like it will be like small text will be there. But
Yeah.
if they are in full screen mode, then it is okay. They will be able to see the presentation easily. So that is the point.
Okay.
Yes, sir. Yes.
Okay. Okay, fine then. I think
Yes, sir. Yes, sir.
that's.
We will again come. I think at 2 p.m. Thank you, sir. Thank you very much.
Thank
Yes,
you.
sir.
Thank you.
Yes, sir.
Thanks.
Hello, Eric, sir.
Yeah.
Yes, sir. That day, I think we were not able to check the screen sharing. Can we check it now?
Yeah.
Yes, sir. Yes, sir. We can just have a check and then we will again come at 2. On. Yes, sir.
Oh, you seeing my screen?
Okay, sir. Yes, sir. It is visible. Yes, sir. It is definitely visible. You just change the slides like uh, present in share screen slideshow mode, and yes, sir. It is now there. But can we do it in slide sharing so that we can get that idea also?
I think
Like you just share the slide from top down. This slide sharing. Yes, sir. Yes, sir. Yes.
it is for me. It is we are sharing the screen. Yeah.
Yes, sir. I am also seeing the screen, but I am seeing the whole window of the PPT. Like a PowerPoint window, I am seeing all the window. I am wanting to like it should be shown in like full screen slide sharing mode. Hello, sir. Are you getting my point?
Yeah.
Yes, sir.
I'm
Yes, sir.
trying to
Yes,
understand.
yes, sir.
Yeah, I'm trying.
Sir, just to make it slide sharing, and we will just check if it is okay or not. It will be definitely okay, but let us do one time only like this.
I'm trying to find where is the slide sharing.
Sir, you just go to top down, like lower
Vikas,
corner.
can I help him? 1 minute.
Yes, sir. Yes,
Dr.
sir.
Eric,
Definitely, definitely.
Dr. Eric, what Vikas is trying to say, you have to go to the presentation mode. That's what he's trying to
Yes,
say.
yes, sir.
But I'm in the presentation mode.
Okay,
No,
but
I
it is
think
not
it's
coming. Yeah.
so you have to
It's not.
go to the bottom right where you just go to the full screen.
Let me go back. So partager full screen.
No, sir.
So
You can just do on. Okay.
I'm sharing my screen.
Yes, sir. It is visible.
What are the screen you have in line right now?
In the bottom right, you will
In the
see
bottom right, there is a
minimize in left side or the minimize button. The minus button
in the
in the
bottom right there is like wine bottle type structure. You just click on that.
I'm trying to look at that, so sorry about that.
There
Sir,
is
can we do
plus
for
and
you
plus
as an
sign,
example?
and the right bottom plus and minus sign, and
Sir, there is zoom in basically in the bottom right. So just left to that is a one button. You just click on that.
So that one.
Yes, sir. Yes, sir. Yes, sir. Definitely.
So we are. This is the right one for you.
Yes, sir. Yes, sir. This will be in presentation mode now, but it
Yeah,
is
yeah.
not coming till now. I think it is lagging. Let's wait for 1 to 3 seconds. Oh, it is not coming.
Let me share. I think I have to share another screen. It's
Sir,
not
can
the
we?
right screen we are sharing. Hang on, hang on.
Okay, sir.
We do something.
Sir, can I show for an example? Like,
Yeah, yeah.
but that I will do also the same thing, but I am doing it right now. Yes, sir.
what are you meeting conference?
Sandeep, your voice is coming. Can you unmute yourself? Mute yourself basically. Okay. So, sir, I am sharing my screen basically. I am sharing my PPT PowerPoint presentation.
Yeah.
Is visible now, sir? Are
Not
you
yet.
able to see it? Okay, it is
Not
coming.
yet.
Now it is visible.
Yeah.
And sir, there is this slide show mode. Basically, you have also clicked on
Yeah,
it,
yeah. So
and this will change into this.
yeah. So I did that already. Yeah.
But sir, from our side, it was not visible. Like full screen was not visible. We are just able to see
Yeah.
the.
Because
Yes, sir. Yes, sir.
yeah.
Yes, sir.
Because I'm not sharing with you the right screen. I have two screens in front of me.
Okay,
So
sir. But we are wanting that screen, basically large screen,
yeah.
so that
Yeah.
participants will be easily able to see the.
I
Yes, sir.
got this point for sure. So
Yes, sir. Yes, sir. Definitely. You already know. I don't know why I'm telling you this point.
hang on.
Okay, sir. Fine, sir. Then we will see that point later. But it is
No,
screen
no, no.
sharing is. Oh, yes,
Let's
sir.
do it right away. Let's do
Okay,
it
sir.
right
Fine,
away.
sir.
So
Fine, sir.
I'm trying.
I'm stopping the screening sharing.
Yeah.
I have stopped that. Yes, sir. Now it is good. It is
Yeah.
fine.
So yeah. So I'm sharing the
It
right
is
screen
like
with you.
it is like one go.
No, no, because we as I saw, I mean, it was not the right screen that we are sharing, so that's why we were not.
Okay, okay, fine, fine, sir. Now it is cool, and we will come after 10 minutes for the session. So
Yeah.
let's wait for 10 minutes. Yes, sir. Thank you, sir. Thank you very much, sir.
Bye bye. See you later.
Yes, sir. Yes, sir.
Hello.
Hello. Yeah.
Yeah.
Yes,
Is it
Sunil.
Professor Eric? You are there.
Yeah.
Great. Okay. So basically, so this program actually is being live casted on YouTube channel also. So
Okay.
yes, some people are here with us, and some are joining or attending it through the links, external links provided. So basically, yeah, so the first talk is by Dr. Prashant Upadhyay, and then from 2:30, your talk is there.
Yeah.
Sir, we have checked the slide screen sharing basically by
Okay.
Prashant sir also and by Eric sir also. So they are cool. They are fine. Yes, sir.
Okay.
I think it is fine. Yes, sir.
Sure.
Hi, Sunil. Good afternoon.
Hello. Good afternoon, Dr.
Good
Prashant.
afternoon. Yeah. Are we on time to start with?
Yes, yes, definitely.
Okay.
So your talk starts first at 2.
Okay.
So we have like 25, 26 minutes for the talk, and then few minutes for the question answers. But
Okay.
yeah, meaning 25, 30 minutes are for the talk.
Okay.
Yeah, and then we can have, because earlier we had one more oral presentation here in this no, that is still there. Okay, I see. Yeah, so we have like 30 minutes for the talk.
Okay.
So
Okay. Somebody's going to buzz me around 20, 25 minutes?
yeah, I can do that. Yeah.
Okay. Hello, Professor Basu. Good afternoon.
Good afternoon.
How are you?
Good. So we are ready to proceed with the next session, right?
Sure. Yeah.
So Sunil, I think for this session you can introduce the speakers and we'll continue.
Yeah, that's right.
Okay.
Yeah, so just 2 more minutes. Probably some more people can join directly here. Others, I told everyone that some participants are there who are watching it online on the YouTube channel.
Can I share my screen right now, or?
Yeah, you can just go ahead to share.
Okay. Can you see my screen?
Yes.
Okay. So there is a lag. Okay.
A little bit, yeah.
So Sunil, we are rescheduling, sort of changing the order, or?
No. I mean, I see the program that is there on the web. As per
Yeah,
that
Prashant
program.
Upadhyay. Yeah, where is
Yes.
Dr. Upadhyay? You are here, right?
Yeah.
Yes.
Oh, yes, there you are. Yeah. Okay.
Yeah, so basically now we can start. So welcome to this session, second session of, second part of this session after lunch. So in this one, we basically have 4 invited lectures and 1 oral presentation. And we will be concluding the session at 5:30, after which there are some post session things to be discussed. There also all the participants are welcome to attend. So we will start this part of the session with the invited talk by Dr. Prashant Upadhyay. Dr. Upadhyay is with the ISRO Bangalore. He is leading a team that is working on the development of precision atomic optical systems, particularly atomic frequency standard, that is atomic clock and atomic magnetometer for ISRO's future space missions. Dr. Upadhyay completed his PhD from University of Cambridge, and subsequently he spent many years in University of Leeds, UK, and also at Los Alamos National Laboratory, LANL, USA. For many years he was there. His current research areas basically are, they include ultrafast laser spectroscopy, terahertz technology, condensed matter physics, nanophotonics, atomic physics, and so on. And today he is going to share with us some of his work that is on terahertz technology for the space applications. So I invite Dr. Prashant to deliver his talk, please.
Thank you, Dr. Sunil. Thank you for the kind invitation to talk on terahertz technology for space applications. The terahertz initiative in ISRO is quite recent, and I'm currently from Laboratory for Electro-Optic Systems, which is a unit of Indian Space Research Organization in Bangalore. I'm going to talk about some of our recent initiatives in the later part of my talk. To begin with, I'll be talking about some of the interesting terahertz phenomena one can expect to see in space, and some of the terahertz instrumentation that's available to explore the terahertz dynamics in space. So if one wants to look at the earliest terahertz phenomena available in space, you have to really go back in time. You have to go back in time to all the way to Big Bang. That's where, as we understand today, the time started. And right after the Big Bang, as many of you know, that there was the primordial plasma, which primarily contained electrons and protons, which are the elementary particles, and also a wide range of radiation, electromagnetic waves. So this plasma, like a fog, dense fog, where this electromagnetic radiation could not escape out of this plasma because of multiple scattering within the plasma. And the whole universe, in the early stage of the development or evolving, it looked very opaque. So over the time, the plasma expanded, and the temperature of the plasma cooled down. So as it cooled down, the more and more the formation of the neutral atoms. The first atom which was formed at the back in time, it was the hydrogen atom. As the neutral atoms were formed, some of these radiations were able to escape out of this plasma, traversed in space, in time, and that we can even see even today in the present time. This picture represents the time starting from the Big Bang all the way to the present day time. So in these, the time axis, there is a time right after the Big Bang, around 380 years after the Big Bang. As I said, the plasma was cool enough to enable the formation of the atoms. So the radiation which escaped out of this plasma and then permeated through the space, it is still traveling in space and it's surrounding us and making a background. This background radiation, which originated back in that time, available for us to look around today, surrounding us, this background is making us a background, which is the cosmic microwave background. Why it is called the cosmic microwave background? So that primarily depends on what kind of energy spread is this cosmic microwave background is forming. If you look at the energy spread of this microwave background, it's somewhere starting around 0.1 millimeter to all the way to 10 millimeters. So this is typically the microwave frequency range. And the way the radiation is distributed, it's like the black body radiation, take it at 2.7 K. If you know the black body radiation as function of temperature, so higher the temperature, the radiation peak intensity shifts to higher frequency. As you can see at 6,000 K, the black body radiation is peaking around visible region. As you go down in the temperature, the peak intensity of the black body would shift to the lower frequency of the longer wavelength. That's how what you see at the 2.7 Kelvin, that peak of this radiation intensity, it is around 1 millimeter, which corresponds to 0.3 terahertz. So that's why the cosmic microwave background, it represents the terahertz, the background itself. And this radiation is extending even beyond 0.6 terahertz. That's one other interesting fact about the terahertz. Other than this CMB, the universe is also containing some submillimeter wavelengths peaking at 3 terahertz. So that means we are actually in the pool of terahertz radiation surrounding us. So it's only depends on how you look at these things. So then only you can see what kind of different things are visible to us. So if you take a unit or an instrument which can give you an image at visible light, or is around 500 terahertz, then this is what you see. Instead, if you have an instrument which can give an image of the universe at 1 terahertz, the image of the sky, picture is totally different. So what it tells us, the different phenomena, energetic phenomena that exist in the universe, and we have to select the right tool at the right frequency or the right wavelength to look at it. And terahertz is one such frequency where you can get totally different, picture of the universe. So having said that, what is this frequency range what we're talking about? What it compares with the other region in the electromagnetic spectrum? So here is more or less the overall the frequency spectrum. And looking at the higher frequency, you have the UV or the gamma or the X-rays or the infrared. And when you look at the lower frequency, it's the microwave. And terahertz, it's the interconnect between the two. And it's basically the bridging, the region where you access through the electronic means and the region where you access the photonic means. So this interconnect is the terahertz. It corresponds to, in time, it's basically 1 picosecond or 300 microns. What are the dynamics one can expect in this entire frequency range, if you look at it? So in the higher frequency, the visible or the UV, you can expect the electronic transition in the atoms. And when you come to the infrared, where you can see the stretching modes, vibration modes, for example, carbon, hydrogen, or oxygen, hydrogen. You go to the lower wavelength or longer wavelength and the lower frequency, you look at the molecular rotations. When you come to the terahertz, it is the torsional motions of the bigger molecules, collective vibrations of these molecules, or hydrogen bonds, which is the intermolecular bonding between the two molecules. And if you look at more carefully what these internal molecular vibrations or intramolecular vibrations, you look at the bigger molecule, whereas in this case, for example, a molecule containing multiple benzene rings, and it's stretching on a plane, the bending of this plane corresponds to a frequency which is in the terahertz range. Or you can have a torsional motion or rotation of this molecule, especially around these carbon bonds, carbon-carbon bonds. Or you can also have the vibrations along the hydrogen bonds. These are the very weak bond between the two molecules, and bonding is involving the hydrogen of one atom to the another atom in the neighboring molecule. and it could be the influenced by the presence of other intramolecular modes as well. Now, because of the wide signature of these molecules in the terahertz frequency range, one can expect to see the terahertz signature if you have the right tool to look at the atmosphere, and particularly between the frequency range 0.1 to 10 terahertz. The atmosphere has a lot of the molecular distribution, like the water, the moisture, the carbon monoxide, or the oxygen. So especially the water, if you look at it, there are a lot of signatures in the terahertz frequency range. So it's a nice tool to look at it, to this the atmospheric distribution of different molecules. And if you look beyond the Earth atmosphere, even if you look at the interstellar cloud, for example, here, the rotational spectra of the Orion Nebula, where it is showing a lot of spectral fingerprints of diatomic as well as polyatomic molecules. So that gives us a wide range of applications, even if you look at beyond the Earth's atmosphere. For example, if you look at our planetary system, comet, for example, the comet is also has a lot of water content in it, and this is one of the study of a comet Hartley 2, this Herschel Space Observatory, where you can see the existence of two types of water. One is the heavy water, and other one is the normal water. And probably by comparing what the signatures of or the molecules, water molecules that exist on these comets, you can compare them with what is available on the surface of the Earth. Probably we can arrive at some sort of an understanding where the probably the what that we see on the Earth would have arrived from. And the other thing is more detail into the atmospheric study, where you can also understand the changing climate, for example. So here is an example where people have studied the ozone layer as function of altitude as well as the diurnal change. So not only the ozone, but also we are studying the carbon monoxide, the acidic molecules that exist in the atmosphere, which could be detrimental to some of the issues that related to climate change. So here, this ozone was studied using this instrument called the terahertz and submillimeter limb sounder, which is basically a multi-channel cryogenic heterodyne spectrometer operating in the range of 1.8 terahertz to 0.6 terahertz. So you can also look at one of the biggest objects in our solar system, which is the sun, where there are some of the surface-related activities on the sun, like the solar flares. What are the solar flares? These are the sudden explosion of energy from the surface of the sun due to the very high intense magnetic field, localized magnetic field. And sometimes the solar flares can be accompanied by the coronal mass ejection, which is called the CME. So this combination of these two are very, very deadly. And sometimes if they reach the surface of the Earth, they can interfere the power utility grids, causing the electricity shortage and also interruption of the communications as well. So what is the relationship between the solar flare and the terahertz? That lies in the energy spread in the solar flare itself. If you look at the energy distribution of the solar flare, much of the energy is actually concentrated around the 1 terahertz. So this is what is the intensity of this? Around 5,000 solar flux unit. What is a solar flux unit? Is the conversion is here. So if you have a right tool, terahertz tool, to look at the solar flare, which is placed, let's say, between Earth and the sun, then you can actually detect the solar flare, give early warning to the Earth, and then probably we can better prepare to avoid any of this damage that can potentially cause on this. So there are a lot of other applications for this the terahertz technology in mostly in the terrestrial applications like spectroscopy, imaging, remote sensing, communication, etc., etc. So when it comes to the terahertz instrumentation, one has to look at the terahertz sources and detectors and employ them in constructing the spectrometers and photometers. So there are a whole host of technologies are available to generate terahertz radiation and to detect. So among these two, I'm not going to talk about all of them. So there are the techniques based on photoconducting antenna, the optical rectification. So primarily used to construct the spectrometers, Whereas when it comes to the space application, people normally use, the bolometer as well as the heterodyne detectors. So I'm going to talk more on these detectors because these are more relevant when it comes to space application of this terahertz radiation. So there are two types of detectors of this terahertz, which are considered as terahertz sensors in astronomy. So these are coherent detectors as well as the incoherent detectors. So what are the coherent detectors? These are primarily heterodyne detectors based on this technique. So to give an example of how the heterodyne detectors work in terahertz frequency range, it uses the mixers where the optical frequency from the outer space will get mixed with the local frequency, the frequency from the local oscillator, and produces the sum frequency as well as the difference frequency. And that can be detected or measured using high quality or the low noise electrical detectors. And the other type of detectors we call incoherent detectors. For example, the bolometer, where the radiation or the optical light, the radiation will get absorbed in the absorbing medium. And this absorbing medium is in thermal equilibrium with the heat sink. And this intensity or the power of this incident radiation will change the temperature of this absorbing medium. The change in the temperature is typically measured as the change in the resistance is related to the incoming radiation. So there are different types of bolometers available, as well as there are different types of the heterodyne receivers are available. So if you look at this coherent detectors, because you can measure this electric field of the incoming radiation, you can actually get the amplitude as well as the phase of the electromagnetic field, and that can give you a large photon number gain as well. And one of the good thing about the heterodyne receivers is that it's the ability to provide very high frequency resolution. And the challenge in this case, it's the type of mixes one can use. For example, there are a variety of mixers that are available, particularly to use these receivers in the terahertz frequency range, like Schottky diode mixers, superconductor insulators, hot electron bolometers. I'm not going to go through all of that right now. When you compare the coherent and the incoherent sensors, coherent receivers are best for narrow bandwidth and high spectral resolution applications. And also, they are better at the radio frequencies, like sub-millimeter waves, where the background is significantly larger than the quantum noise. Whereas the incoherent detectors, like the bolometers, they are better at the thermal background limit, like the IR or the far infrared terahertz, and also in the optical region. So what are the benefits of incoherent detectors, like the bolometers? They have the very good continuum sensitivity, like the wide optical bandwidth. And the good thing about this, you can have very low NEP, noise equivalent power, better than picowatt per root hertz. And you can even reach the photon noise limit as well. And there are good thermistors like TES, transition sensors available. But the only thing is, you need a very low temperature. I mean, you need to have the cryogenic cooling to get a good sensitivity from these detectors. So this is the genesis of some of the incoherent detectors which are being employed in the space mission over the years. And in the recent past, people have been using the superconducting these bolometers based on this TES technology or MKID technology. And that looks like the future of the space application of these detectors. Now, I'm going to talk a little bit on some of the initiatives at LEOS, or ISRO in Bangalore. Primarily to construct the terahertz photometer for solar flare detection. Now, this development has some of the challenges. The challenge is to detect terahertz in the solar flare, which is kind of buried in the extensive, high-intense background, which is visible in the IR. So if you look at that spectrum, this is nothing but the background that exists in the solar flare. And that's about 1.37 kilowatt per meter square, whereas the terahertz in that background is only 0.28 milliwatt per meter square. So you have to have very high spectral selectivity of the order of 0.2 ppm. So my colleagues in LEOS, Karanth and his team, they have employed a uncooled bolometer based on this immersed vanadium oxide bolometer detector employed in a telescope with the Cassidrain optical configuration, where you have a concave mirror and the convex mirror, and a couple of the bandpass filters and the terahertz detectors. So this spectrometer, so this photometer allowed the detection of terahertz somewhere in the region 1.5 to 20 terahertz, the low pass filter, and with the band pass filter, we could make the terahertz detection only in the region of 3 terahertz. So this is how the low pass filter that our colleagues made, which can detect anything less than 20 terahertz, and this is the band pass filter. So this filter was achieved by use of the softening of the mirror surface as well as use of Pickle mesh filters. Now, this is the calibration of these filters and how we achieve the kind of resolution. So for this continuous detection, the resolution is about 125 SFU, whereas for the bandpass filter, the photometer, the resolution is about 700 SFU. That's enough to detect the solar flare intensity in the terahertz, which is about 5,000 SFU. These are some of the specifications that we achieved in this photometer. Here you can see the picture of this photometer, and the whole weight of this is about 1.8, including all the housing and electronics, everything. It offers a wide range of things, including the sensitivity around 125 SFU, and even the range of communication abilities, and the size is also quite portable. We are planning to fly this in the upcoming PS4 mission, probably next year or so. PS4 is a PS4 orbital platform where we can mount this and we can test this spectrometer for some of the utility in next generation space mission as well. So there are other space-borne terahertz instruments, also the ground-based terahertz instruments. For example, the Herschel spectrometer, which is a joint between ESA and NASA, where it actually has a lot of the mixers and bolometers in the spectral terahertz frequency range, primarily to understand the life cycle of gas in the dust. And here is an example of one of the images taken by this Herschel heterodyne instrument for far IR, which basically shows some of the water and an organic in Orion Nebula. Likewise, the SOFIA, which is the largest airborne observatory in the world, and the spectrometer is housed in an aircraft, and it flies across this stratosphere, and one can study the complex molecules in space and the starbirth and the depth of the star like that. And this instrument in this SOFIA also covers wide range of frequency, 0.4 terahertz to 30 terahertz as well. ALMA, which is the ground-based sub-millimeter array antenna as well as telescope instrument based in housed in Chile, South America. And also it can also study some of the physics of the cold universe. Now, in the last leg of my talk, I just want to focus a little bit on some of the initiatives in India on studying the cosmic microwave background. There have been some of the missions in the past by different space agencies, starting way back in 1962. That's when the microwave background was detected by Penzias and Wilson. They got the Nobel Prize in 1978 as well. Then NASA taken up this COBE, and after that, that was in 1989, to study the temperature distribution of this cosmic microwave background. Again, way back in 2001, there's a Wilkinson microwave anisotropy probe, which also studied the microwave background. And quite recently, the Planck mission in 2009. And that actually mapped the whole cosmic wave microwave background to an accuracy of the resolution of 5 arc-minute. And this is some of the Planck images, and that was taken in 2015 and taken at different. This images indicate the temperature distribution in the cosmic microwave background at different frequencies. When you image it at 30 gigahertz and all the way to 857 gigahertz. So, what is the initiative in India? there is a link with the initiative in India, also the recent initiative taken up in Europe, which is called CORE. It's nothing but it stands for Cosmic Origins Explorer, where the group of people in European community, they proposed this mission to the ESA, and it still is not materialized yet, probably. But the same set of people, together with some of our colleagues in India, they have proposed a possible ISRO-ESA joint CMB mission. It was submitted in 2018, and there was a consortium also formed in India called CMB Bharat, where this consortium is led by Professor Tarun Sauradeep at Icee. So a lot of discussions have happened in ISRO as well, along with the people from core team, Jackie and Francois. And I think hopefully there will be some sort of convergence on this the optimistic and very massive project and mission in the near future as well. So what is the motivation of this mission, the proposed mission? This proposed mission is primarily to understand the distribution of the CMB radiation as well as its polarization. So I'm going to talk about in the next slide, what is that polarization, why it is significant. So what is the promise of this? Probably we're hoping that we can understand more of the quantum gravity as well as the ultra high energy physics in the early universe. And also probably can have a better understanding of the cosmological model. And probably we can map the dark matter in a better way and also understand the baryons. So basically we can probe the entire thermal history of the universe. So why the polarization? So again, we have to go to the Big Bang. So around the Big Bang, the one other thing also is interesting is the gravitational waves. So the Big Bang, rapid expansion of the universe around that Big Bang, immediately after the Big Bang, probably would have produced some of the gravitational waves. It is yet to have a conclusive evidence on this, and this gravitational wave produced around the Big Bang probably would have stretched and squeezed the primordial plasma at the time, inducing motion in the spherical surface that emitted CMB. And because of the stretching and the squeezing motion of this plasma, that caused the redshift and the blue shift in the cosmic microwave background. So that redshift and blue shift has polarized the cosmic microwave background. So if you study this polarization effect, you will understand not only the cosmic microwave background distribution itself, but also some of the origin of these gravitational waves that would have generated during the Big Bang. And that probably helps us understanding the whole evolution of the universe. Now, they proposed this CMB mission has some of the design of the telescopes, as well as some of the other spacecraft in the whole instrumentation. It's quite a complex the endeavor. So we have to have some of the passive pullings, and then there's a telescope here mounted, and then we need to have a lot of array of detectors for sensitive detection. So the design of the telescope itself, it's quite challenging, because you have to have a optics that can quite sensitively reflect the terahertz radiation. And also one of the challenges to fabricate or design the active pullers, probably the dilution refrigerators, and also the passive pullers like the V grooves. So these are quite challenging things. And also the detector itself. We have to fabricate the terahertz detectors. So we have to go for some of these bolometer detectors. And not just one frequency, we need to go for an array of detectors covering a different frequency range, anywhere between 30 gigahertz to 1000 gigahertz, 1 terahertz. So plan is to use some of these technology like transitional sensor bolometer detectors, which can have NEP, noise equivalent power, less than even 10 kilowatts. The idea is to launch this spacecraft into the L2 orbit, which is called Lagrangian 2 orbit. Why Lagrangian 2? If you look at this image on the right here, so this is the Lagrangian 2 orbit, which is actually on the right side of the Earth, where on the left side of the Earth, you have the sun, so that you can avoid any background radiation coming from the sun, so that you can sensitively map the cosmic microwave background. So that's what looks like the future. So we'll see what when we get there. Hopefully we'll have some on convergence on this mission as well. So with that, I would like to conclude with the point, many of the energetic phenomena in the universe are in the terahertz region, are still waiting to be unraveled. So because of that, I would say terahertz field continues to be the holy grail of future space explorations. With that, thank you very much for your attention.
Thank you, Dr. Prashant. So the talk is now open for questions if there are any. Vikas, do you have a question?
Sir, basically, hello, sir. Hello, Prashant, sir.
Yeah.
Here is Vikas. I was asking, like, there are different techniques to measure this cosmic microwave background radiation. Like you have shown the comparison table, basically. So, what is the what criteria we choose for measuring this birefringence properties for this cosmic microwave background radiations? Which technique is good for that?
Yeah, we need to have a polarization sensitive detectors. Okay. So the one of the thing is even in these detectors, we need to have the antenna coupled detectors. So that would essentially enable your the polarization sensitive radiation, and you can detect them quite sensitively. So even with the bolometers, you can actually have this the antenna coupled bolometer detectors. So probably that would enable you to detect this.
Yes, sir. Yes, sir. I just wanting to ask, what is the physics behind that? How they are just differentiating between the two polarizations, basically, in that particular system?
Yeah, you have to basically map the radiation in space.
Okay.
And then you have to understand what is the sort of a distribution in different angles and with the quite a good accuracy, spatial accuracy.
So there will be some kind of steering arrangements for the devices also.
Yes, correct. Yeah, you have to have a steering arrangement for that. That's true.
So how much precision you are getting in that steering also? Like
we don't know that, but I think I mean the plan is this is even planned by the core team as well. Better than 10 arcsecond.
Okay. That is quite low. Yes, sir.
Yes, that is a hope, and that's quite challenging too. 10 arcsecond is not a small number. I mean, it's not that easy to achieve as well. That's true.
Okay. Thank you, sir. Thank you very much.
Thank you.
Okay, so I think with this, we conclude the talk by Dr. Prashant. And thank you very much, Dr. Prashant, for accepting our invitation and giving a very interesting talk in this session today. Thank you very much.
Thank you.
So now we move to the next talk in this part of the session. And it is by Professor Eric Fritz from University of Bordeaux, France. Professor Eric actually is currently the Director of Research, CNRS Director of Research at the University of Bordeaux, where he is leading a group on photonics and material research. In short, it is called LUMA at the University of Bordeaux. He completed his PhD from University of Bordeaux in 1983, and since actually 1984. He is with the University of Bordeaux and CNRS. He spent a few years with the Professor Y.R. Sen at the University of Berkeley as an associated scientist, and has done tremendous amount of work in the area of nonlinear optics, and for quite some time on terahertz spectroscopy and terahertz optics in general. So today, Professor Eric is going to talk about some of the results from his research group, that is on optical and terahertz 2D spectroscopy of conducting polymers. And now the floor is yours, Professor Eric. You can now start. So your mic is muted. You can unmute your mic first.
It is on now.
Yeah, and you can share the screen also.
Okay. Is this okay for everyone?
Oh yes, we are able to see. You can go in the screen mode and then start.
Yeah, so am I in the screen mode? Are you seeing this screen? My full screen or not yet?
Not yet.
Okay, so I have to share this one. Okay, let me see. We are into that share. The right screen that I'm sharing. Sorry about that. So facing again the program. Can we share the screen back? Sorry. Sorry about that. Alright. I'm facing a program.
Yeah, when you have two screens, then these kind of difficulties always come.
Yeah. So that's why I'm trying to avoid
Perfect.
it. So
Now it is there. Yes. Go ahead.
Okay, sorry about that. Thank you, Sunil, for this kind presentation. Thank you for the organizing committee for giving me the opportunity to present the work we did about excited state dynamics of conducting polymers to by time resolve optical anti-Earth spectroscopy. So this work is an ongoing collaboration we have with the chemistry departments at the University of Bordeaux, the group of Professor Adjanou, to which belongs Eric Cloutet and Mrs. Bousquet. So those people prepared the sample that we studied in the LOMA, Laboratoire des Matières d'Aquitaine at the University of Bordeaux, and the work was performed by Frédéric Dutin, a former student of the group, Professor Jérôme Degère, Marc Tondusson, and myself. So as the title indicates, we are going to talk about conducting polymers, and in fact, the conducting polymer we are the conducting polymer we are going to deal with are P-dots-based conducting polymers. So those conducting polymers are based on two ionomers, P-dot, that's the chemical formula is shown here above, and to which we had another ionomer, which is PSS, that the chemical formula is this one. So P-dot PSS is a well-known and commercially available conducting polymer, which has an excellent conductivity and which also presents a good optical transmission when prepared in seal film in the optical range. It is widely used for electrodes in optoelectronics devices, solar cells, OLED, etc. It has also been shown that it has a of neutral density filter with variable optical density. This conducting polymer have, however, some drawbacks, which are related to the hygroscopicity and acidity, which happens as it fixed water. And besides that, it has also some wetting problems, which makes it difficult to spread on organic surfaces. So that's why a few years back, the group of Professor Adjanou prepared another ionomer, which we will call PAN, that's chemical P-dot. P-dot PAN, sorry, was able to get rid of most of the drawbacks which were coming when using P-dot PSS. So it has good performances in the optical range, so in the conductivity, but nothing was really known about his properties in Terz range. And besides that, when such a conducting polymer was excited by short femtosecond pulses to understand the kinetics of carriers in such a conducting polymer. Okay. For some reason, I'm stuck. Okay,
you can use probably the Yeah, the arrow keys of the keyboard.
Yeah. So I have a problem with my mouse. Okay, so we decided to prepare the samples. In fact, those samples were prepared, as I said, by the chemist, and those samples were made out of P.PSS or P.PAN, to which we had a solvent, which is DMSO, and we prepared 500 nanometer thick films that was deposited on high density polyethylene films. So what happens is that as we prepare the thin film and make them dry, what happens is that the polymers form balls which are in contact with each other, and the size of the balls is about 50 nanometer in size. So those balls are in contact. So so the conductivity of such polymers can be described using a Drude-Swiss model. And I will rapidly go through what is a Drude-Swiss model. So a Drude-Swiss model is a model where the conductivity is coming from a conductivity of a Drude, which is related to the two main parameters: the plasma frequency, which is related to the number of carriers, the charge of the carrier, and the effective mass of the carrier, and another coefficient, which is gamma, which is the mean time between two collisions with carriers. So if we look at the Drude-Swiss model at zero frequency, the DC conductivity, you find that the Drude-Swiss model conductivity is the conductivity of a Drude model multiplied by a coefficient which is 1 plus C1. The C1 coefficient can be varied in between -1 and 0. So if we have a 0 for C1, we have the conductivity of a conventional metal. And if C1 is -1, then you have the conductivity which is associated to a bad conductor. So in a conducting polymer, we have a grain of the conducting polymers which are in contact, and which makes more or easy the transfer of carrier from one ball to another. So to account for this difficulty of the carrier to go through the barriers between the two balls, we introduce a C1 coefficient, which will be in between -1 and 0. So the first thing we did was to measure the conductivity of the using time domain TRS spectroscopy. And I'm going to present both the time domain TRS spectroscopy and the optical pump TRS probe setup we use, in which we can also induce a change in the conductivity of the thin film, exciting the sample by pump pulses. So the TRS pulses are generated using femtoseconds, millijoule pulses that are short and about 50 femtoseconds. And those pulses are focused in air. And prior being just after the lens, which is used to focus the beam, we have a second harmonic generation crystal, which makes it possible to frequency double the central frequency of the optical pulse. So at the focal points, due to the fact that we have a very high intensity laser pulse, we create a plasma. And in the plasma, the interaction of the second harmonic field and the fundamental field with the plasma create an intense broadband TRS pulse. This broadband TRS pulse is then collimated and focused on the sample. And then the beam, which is either reflected or transmitted by the sample, is then measured using an electro-optic detection. So the electro-optic detection consists in using the electric field associated with the TRS pulse to induce in a nonlinear crystal a birefringence. So initially, the crystal is isotropic, and when it is excited by a TRS pulse, electric field of TRS pulse becomes birefringent. And the birefringence is measured using a weak femtosecond pulses. Wave plate, a Wollaston prism, and two photodiodes. So since the optical pulse is very short compared to the TRS pulse, so TRS pulse is typically about 1 picosecond length, and the optical pulse is 1/50 second. If you delay one with respect to the other, you can measure the wave of the terrace pulse in the time domain. So the setup can be also used to measure the change in the conductivity. So what we do is we measure the amplitude of the terrace pulse, which is transmitted or either transmitted or reflected by the sample, with and without the pump pulse, and we measure the difference in the amplitude of the electric field. And the change in the amplitude of the terrace pulse makes it possible to measure the change in the conductivity of the sample. So let's see, first of all, what are the conductivity of the sample we prepared in the terrace range. So to measure the conductivity, we have the terrace TDS spectroscopy, and to measure the conductivity, we have to make two measurements. One with a bare sample, in which we let the terrace pulse go through, and one with the sample on which we deposit the thin film. In the middle of the view graph, you have the terrace field, which is transmitted by the bare sample, the substrate, which is high density polyethylene, and with the substrate on which we have deposited the thin film, and the terrace pulse is in red. And you can see, even though the thickness of the film is quite small, we have a huge change of the amplitude of the terrace pulse, which is transmitted. So if we make the Fourier transform of those fields, we have the different spectral components of the terrace field, which is either transmitted by the substrate on which we deposited the sample. I have it. So if we can accordingly compute the transmission at each spectral component, and knowing the transmission at each spectral component, we can compute the conductivity of the sample at each spectral component. To do so, we need to know, besides the transmission, we have also to know the index of refraction of the sample, the substrate, its thickness, and the impedance of vacuum. So let's see the result we got for P.PSS and P.PAN in the terrace frequency range. So you have on the left side, you have the P.PSS, and the right side, you have the P.PAN. And as you can see here, the conductivity is a complex number. We have the real part and imaginary part of the conductivity. For the imaginary conductivity, in red, you have the results of the experimental data, and in blue, the results of the fitting. So for the real part and the imaginary part, we have a good conductivity. We have a good result. We can, let's say, properly fit the data. And 2 points that should be noticed. The P.PAN on the right side of the picture and the lower pan, you see that we have a conductivity, imaginary part of the conductivity, which is negative. And this can only occur if we consider a Drude-Smith model. For a Drude model, the imaginary part of the conductivity is always positive. This is the first thing. The second point to notice is that if we compare either the real or imaginary part of P.PSS compared to P.PAN, we notice that the conductivity of than P.PAN conductivity. So P.PSS has a higher conductivity. The fits we perform makes it possible to infer 3 parameters: the plasma frequency omega p, the constant time between collision gamma, and the conductivity parameter C1, which is indicating. And you notice that for P.PSS, the parameter is closer to 0 than P.PAN, which is indicating, as we notice here, that P.PSS has a higher conductivity. But we can also deduce another parameter, important parameter from those fittings parameter, which is the DC conductivity. And notice that the DC conductivity for P.PSS is about 3 times higher than the conductivity of P.PAN. So this parameter has been compared to the DC conductivity we experimentally measure using the 4-point methods. And what was very interesting to mention here is that you may notice that the difference in between what we computed from the model and what we measured or very close and within less than 1%, indicating that indeed the model catch up the conduction properties of PDOT-PAN or PDOT-PSS. So far, we have been focusing on the conductivity of those materials, but we don't know exactly what are the mechanisms in play in such a structure. So I would like to what happens and what are the mechanisms taking place and accounting for the conductivity in those conducting polymers. So you have in red the building blocks of the polymer chain, and you have always some counter ion in the structure to stabilize the electric charge. And those counter ions behave like holes and are responsible for the doping of the conducting polymer. So what happens is that as the carriers, as a building block vibrates, what happens is that you have a quasi-particle, which is a mixture of vibration in connection with the carrier, which are moving along the polymeric chain. So this is a polaron conducting. So what happens is that as in material, as a building blocks vibrates, the carrier moves along the conducting polymers. In fact, the number of carriers are so large in P.PSS that you can have also bipolaron, which are moving together along the polymer chain. And in P.PSS, it is the bipolaron, those quasi-particles, which ensures electric conduction. Those polaron and bipolaron have a signature in the spectral range of the P.PSS. And for P.PSS, the polaron are in between 600 and 1100 nanometer, whereas the bipolaron are above 1100 nanometer. So the absorption is very similar for P.PSS and P.PAN. So we may consider that indeed polaron and bipolaron have almost the same absorption band in P.PSS and P.PAN. So what we want to do now is to see what happens to those carrier dynamics as we excite the sample at the optical at the bipolaron in the bipolaron frequency range. So the idea is we want to excite the sample, change the carrier density somehow, and see what happens to the conductivity of the material upon excitation versus the delay between the optical pulse and the Tales pulse we use to sample the change in the conductivity. So what I should mention here is that the time resolved Tales spectroscopy is a bit tricky in this case because we have 3 pulses that has to be accounted in the experiment. You have the optical pump pulses, you have the Tales pump pulses, which is centered at a given time, and you have also the scanning pulses, which is revealing the Tales pulses. So if you want to perform properly the experiment, you have to adjust properly the time scale in between the pump sampling pole and manage properly the arrangement to be able to infer the conductivity. So in the experiments, what we will do is that we will measure the change in the amplitude of the Tales pulse versus 2 parameters. The first parameter, which is tau p, the time in between the exciting pulse and the sampling pulse, and the other time, which is tau s minus tau p. So the time in between the maximum of the Tales pulse and the time of the sampling pulse. So if you do properly this experiment, it is possible to show that the change in the conductivity versus tau p, the delay between the optical pulse and the sampling pulse, you can have this for all the spectral component of the Tales pulses. I'm not going through too much details, but what is important to keep in mind is that you have to be able to measure the change in the conductivity of the Tales pulse. You have to perform, first of all, a time domain TR spectroscopy, static, and then perform a time resolved TR spectroscopy. So what I'm going to show you is what happens as we perform properly the experiment. So we have a two time delay, one which is the time at which we excite the sample and the time at which we sample the signal. So we have a 2D sample. On the left side, you have the different frequency components of the conductivity versus the delay between the optical and probing TRS pulses. And as before, since the conductivity and image, we can perform this for both the real and imaginary part of the conductivity. For P.PSS, the change in the conductivity is very small and about 0.5%, whereas for P.PAN, it is higher and about 2%. So now what we are going to do is to analyze the change in the conductivity at different frequency, at the different frequency components of the TRS pulse versus the delay between the optical pump and TRS sampling pulses. And to do so, we are going to fit the data using the Drude model. So what I'm showing you is the change in red of the imaginary parts and in black of the real part for different delay time between the pump pulses and the sampling pulses of 0.2, 0.6, 0.8, 1.3, and 3.6 picosecond. And we have fitted this data using a Drude-Smith model, which was giving us a reasonably good agreement between experimental data and theoretical data. So according to those fittings, we were able to extract different parameters, which are the plasma frequency, the change in the plasma frequency, the change in the collision time, and the change in the C1 parameter. So all those coefficients are very small, and the amplitude, the change of the amplitude of the coefficient are very small. And we did that for P.PSS and for P.PAN. What should be noticed is that if the change in the carrier density is very small, you can directly relate the change in the carrier density to the change of the plasma frequency. So hereafter, the change of the plasma frequency versus the delay time and try to understand what is going on. So here are the results in the diamonds or the experimental data, and in red and purple, you have the result of the fit, which was considering that the sample has some response time and a Gaussian instrumental response function. So if we fit our data, we were able to get the change in the carrier density versus the delay time between the excitation and sampling. And for P.PSS, we found that we were able to nicely fit our data considering two time constants, one of 0.2 picosecond and one of 1.24 picosecond. For P.PAN, we had to use three time constants, one about 0.3 picosecond, one about 1 picosecond, and one about 4 picosecond. So it seems that we can describe the change in the conductivity of the sample, considering that we are in the ground state, exciting the system in an excited state that relaxes back to a weakly excited state that go back after a given time to the ground state. But the question is, what are those excited states, E1 and E2 star? And to have a better idea of what is going on and what are the nature of those excited states, we did an optical pump, optical probe experiment. So the experiment was performed as before. So we still excite the sample at 1.2 micron. And now we are going to probe the change in the absorption of the sample along the parallel absorption at 800 nanometers. So it was a conventional optical pump, optical probe experiments. And the optical pump was about 120 femtosecond, whereas the optical probe was about 50 picosecond. And here is the result of PSS. And you see that upon excitation, we have a rapid increase of the absorption at 800 nanometer that can be well fitted considering that we have a relaxation with two constant time, one about 0.2 picosecond and one about 1.2 picosecond. And this has to be compared to the constant time we obtain through time domain terahertz spectroscopy. And you see here that the time constant are about 1.2, 0.2 and 1.4 picosecond. So let's see what is the mechanism taking place. So upon excitation, we consider that we are breaking bipolaron. So since we are at 1.2, we break the polaron and we created very hot polarons that are fully within 1 picosecond and which afterward recombines to bipolaron in between in a time constant of 1.2 picosecond. So this seems to be quite good and a good agreement with what we got making the time domain terahertz spectroscopy and optical pump terahertz probe experiments. However, as we did the experiments in P.PAN, we haven't that good agreements between the two phenomena, indicating that at least in this conducting polymer, the mechanisms are not exactly the same. So now I will conclude. So we have studied conducting polymer using terahertz spectroscopy. We have seen that we can fit our data modeling the conductivity using a Drude-Swiss model. A transient terahertz spectroscopy makes it possible to measure the transient and non-equilibrium change in the acid conductivity. And we have also proposed a mechanism accounting for the change in the conductivity, which seems to be good for P.PSS, but not that good for P.PAN. Thank you for your attention.
Thank you, Professor Eric. Yeah. So yeah, the talk is open for questions if there are any.
Sorry, probably I missed the point. What is the excitation density for an optical pump in terahertz probe?
So in this case, we were using, typically, I think it's about 30 microjoule per square centimeter.
Okay, so you're not hitting the nonlinear regime in terms of the carrier density.
No, we plotted the change in delta n versus the intensity, and it was almost linear.
Okay, it's in the linear. Okay, thank you.
I also had a question related to the time domain fitting of the optical pump terahertz signals. If you could go to that particular slide.
Hopefully I will be able to go through because I was facing many problems.
Yeah, I mean the next one.
This one.
No. I mean the next one.
This one?
Even after this. After that. Yeah, this one. So, I mean, if I see your the red one is shifted temporarily. You know, so what is the reason? I mean, like because your fit function that you are using is a summation of exponential functions. And for those exponential functions, the time t equal to 0 should be the same. But your functions seem to have, I mean, the ones which you have shown here seem to have different time t equal to 0.
In fact, so first of all, what happens is that we excite the sample, and during, the response, due to our, Gaussian instrumental response function, it takes some time for the polaron to be, the idea is the following: we excite the sample, and it takes some time for the polaron, for the bipolaron to be broken.
Mm-hmm.
So that's why you have the red curve, which is equal to 0 and slightly increases. So the density of polaron increases, and afterwards, those polaron are recombined and to bipolaron and slowly relaxes. So for me, the red curve has to be delayed with respect to the orange, the orange curve, which is the formation of the the breaking of the bipolar. Am I clear?
Yes. Yeah. Okay. I see. Yeah. So if there are any further questions from the audience. So if not, then let's thank the speaker for a very nice talk. Thank you, Professor Eric, for
Thank you very
delivering this
much.
talk. Thank you very much.
And sorry for the for the problem of the
Yeah, they
presentation.
always, they're part of,
Yeah,
they're
sorry.
always there. Yeah. Okay, so now we move to the third talk in this part, and that is the oral presentation by Yehov Young, which I mean, this is this paper will be presented by Professor Ranjan Singh, if he is around.
No, sir, he is not present yet. So
Okay.
we can move to next, and then we can wait for that also.
No. So in this session, actually, we had in this part of the session, we had the last one by, last one by Professor Ranjan Singh. And the next one will start at 4:30. So we have a break actually before we start the, after this one, the invited lecture 6 starts only at 4:30.
So, sir, we should wait, or we will be here and we will be waiting for Ranjan Singh sir also. Yes, sir.
Yeah, let's wait for him to join. If he knows, right? This time was
Yes, sir.
updated on the web, and he knows.
Yes, sir. Yes, sir.
Okay. Yeah, if he joins us, that's good. If he doesn't, then our next invited talk is at 4:30. So we will gather here by 4:30, and that the talk, scheduled talk at 4:30 is by Professor S.S. Prabhu. So we have two talks at 4:30 by S.S. Prabhu, and then the last one in this Terhart session is by Professor Rajiv Kini at 5 o'clock.
Hello, Professor Sudhir Kumar. Good afternoon.
Hello, good afternoon, Professor Prabhu.
Can you hear me? Yeah, thank you. So I just wanted to check if everything is working fine. So can I just share my presentation and just to ensure that everything is running okay?
Yeah. Please go ahead.
Okay, I'll just do that. So that okay, and I'll just run it. Okay, everything is visible to you?
Yeah, we are able to see everything nicely. Only thing is that there are some gray boxes which appear on the slides. I don't know whether they are intentional or.
No. It should be clean. Is this clean now?
No, it is clean. Yeah, it looks like, oh, those boxes you had put intentionally. Okay.
No. Those boxes, what had happened is all your images and everything, all the attended people, that
Okay.
window is coming in between, which I think it probably makes it
Sir,
as
that
a
is
black.
basically participating candidates are there. So
Yes.
you just
Yes.
minimize it or click on
You
the.
can minimize it, I think.
Yes, sir.
Yes.
Now it is like bar.
It is now,
You can just
so
move it to the corner of the screen also.
yeah. Now it is out of the screen. Now you
Yes,
should
sir.
not see it all. Okay. So just wanted to take that. Thank you, sir. Thank you so much. And
Yeah.
I will then see you at 4:30. So 4:15 or so, I will log in again. Huh?
Okay. Yes.
Okay, thank you.
Thank you.
Bye.
Thank you. Yes, this email was sent to Professor Ranjan Singh or not? That
Yes, sir.
his
Yes, sir.
poster.
We have already sent the mail. I think in the previous for before like 3 to 4 days before also, and also we have sent this time also.
Okay, so
We have sent the reminder also.
But did you? It is not in the. His name is not in the presentation list.
So what happened is that the posters that we had accepted, out of those, a few posters were selected for oral presentation, and this was one of them. And yeah, so what we have done here is that we have included the name of the, the name of the first author.
Oh.
And yeah, so the lead author in that paper was Professor Ranjan Singh, and what we learned is that Professor Ranjan will be presenting it on behalf of the first author. But yeah, so somehow I don't know whether this there was some miscommunication or something, but we were expecting Professor Ranjan to know this and present this paper today. But probably there was some miscommunication.
So his talk was there yesterday, is that correct?
That was in a different session, basically plasmonic session or something. Yeah.
6G, 6G, yeah. 6.
Yes, yes.
But very nicely organized conference. Congratulations.
Oh, thank you, thank you. Yeah, this is for us. It is, the first time experience kind of thing.
Yeah.
And particularly,
all 6, 7 parallel sessions. It's a very big task.
Yeah. Yeah. In fact, the more work is actually with the poster session. Because you are not interacting physically, so what we did is we gave 5-6 minutes to each participant, and sometimes that is not enough. So probably we need to find a mechanism by which this could be made more interactive, basically.
Okay, so for that, the way to do it is, I had attended one of these conference where the poster session was also virtual. So what they had done was, right now, just the way you are seeing your screen, all the attendees. So there you will see the same kind of big hall will be there. Some virtual hall will be there. That virtual hall will have virtual windows or rooms. And in each room, there will be 4 coaches or chairs, you can say. And the first chair will be occupied by the poster presenter. So that poster name will be there, and the poster presenter has to be present in that particular room. And then depending on your interest of that, you can go on from each room or each poster. And once you click on that, then you enter that room. So out of those 4 seats, you will occupy one of those. And then you will start seeing the you can start communicating with that person who is presenting that poster, and you can ask him question, or he can show you on the screen what he has poster, etc. So it was like that, very nicely made. And you can have several floors of this. One floor has this, another floor, third floor, fourth floor, like that. Depending on the theme, you can have different floors. So they're all virtual, but it's really nice. So you can think of that, something like that. Because this will now become a official sort of feature for all conferences. Because next 2-3 years at least, this corona will continue. So most of the conferences will be preferred, virtual one also. So people may not travel that much. So
that's true.
this will become a feature available as a poster session. So you can try that. Of course, presentation is also a good idea, but this is another one where you don't have to, where you have something like 100 posters. There is no point you spending 500 minutes, in the presentation, even if you give 5 minutes to each. So instead of this is the best way that those who are interested can only go to that particular poster and ask. So it works very well.
Okay, I see. So I think we will discuss this with our conference, meaning the manager, basically.
Yeah. I think that would be really nice. They really have a very nice. I think it should be possible for them to do it.
Possible for them. Correct. Yeah. That's right.
So we are waiting for Ranjan, otherwise.
Yeah. Otherwise, yeah. So probably we can a break, and then your talk starts at 4:30, so we can finish our coffee, tea, and things like that, and come back at 4:30. Yeah.
Okay, so 1 hour, yeah. Okay.
Yeah.
All
Yeah.
right. Thank you.
Yeah.
Bye.
Okay. See you.
Hello, good evening, Professor Sunil Kumar.
Good evening. Hello.
Hello.
Hi.
Hi.
So
So I
basically,
think, yeah.
so yeah, you can start sharing. Exactly. Some box. Okay. No, this has disappeared. The box has disappeared. Fine.
Yeah, that is basically that we discussed. No? That was basically the images of other participants and other those things were coming. Nothing else.
Right. Okay. Great.
So you can this will ease out my introduction.
Yeah, very nice. So very good. So I can read from here. Yes. Okay. Yeah, so basically, because this program is being telecasted live on the YouTube channel of the institute. So, yeah, some of the participants actually are there who have logged in as a guest. Yeah, there is some other account. So, because of that, they will not appear here in the list.
Oh, okay. Because I saw something like 17, 18 people. So normally it happens if you have a large number of sessions, parallel sessions, then the total number actually becomes less. So that and only specialized people only come and attend.
That is true.
So that way it is a good thing. You only have people who are interested in that.
Yeah, that's right. So yeah, so some of the interested participants might be attending it through the live YouTube channel. That is what I wanted to say.
Yeah, sure, no problem. We can also take questions from YouTube. So I will try to stop 5 minutes before so that you have 5 minutes question answer whatever.
Yeah, that's right. So like 25 minutes we can have the talk, and then last 5 minutes we can basically take the questions.
Yes.
Okay,
sure.
perfect.
And CD is going to speak no after me.
Yes. Kinney will be speaking. That's right.
Yeah.
Kinney has not joined yet, but probably he may join soon.
He join little later.
Yeah. So okay, so probably we can start now.
Okay.
So so welcome back after the tea break. Now we have two talks basically. The first one is by Prabhu, and the second one after 30 minutes from now will be by Professor Kinney. So Professor Prabhu is with the TIFR Mumbai, from where he completed his PhD also many years ago. And actually, meaning when you talk about terahertz science, the research and technology in India in particular, then Professor Prabhu doesn't need an introduction. Everybody knows about Professor Prabhu and his contributions in this area of science. And his nature is so pleasant that, with whomever he talks, even for, everybody becomes a fan of Professor Prabhu, including me. So, I remember when I talked to you for the first time. I was a PhD student in Icee Bangalore, and I was visiting TIFR Mumbai for a CEFIPRA meeting. And I was speaking about this terahertz spectroscopy and so on. So we had that brief interaction at that time when he was attending the meeting. So you were in the audience, and I was the presenter at that time. So now we have we are very glad that you accepted our invitation to talk to us today. Yes. Professor Prabhu is going to talk about terahertz spectroscopy and metamaterials in terahertz, a review. So yeah, so it is now, Professor Prabhu, you can start now.
Thank you. Thank you so much, Professor Sudhir Kumar. It is a great pleasure and great honor. And thanks for inviting me to give and also giving me this opportunity. I also had a very nice experience during the tutorial. It was very nice. Large number of students attended it, and it's a very wonderful organization by Professor Sunil Kumar and all this big team. I congratulate you all for very nice arrangement. And so I hope that this experience will also enrich you with a lot of management and other things of these big events. So
Yes,
with this,
definitely.
thank you so much. And do visit TIFR. You have a standing invitation whenever everything gets back to normal or whatever. So do
Yes,
visit
sure.
TIFR and I
Sure.
will show you around the laboratory. This plan of my talk today will be, I'll just briefly talk about the terahertz properties, advantages, limitations, and I will mainly talk about the photoconducting antenna work. Some part of it I have already covered in the tutorial, but here I will talk a little bit more detail. And then I will also speak about our metamaterials studies, and we have also built this near field microscope. So I will also give you some of the glimpses of that. These are very new results. So of course we are working on it, and once it's published, I think we will have much more to talk. So basically, what is terahertz? The terahertz lies between this electronics and photonics. So most of you we are already familiar with this, and this is a region which is still unexplored in the sense that people have last 20 years have started exploring it, but there are no high power sources in this, and that is why it has been a big problem. And that's the holy grail to have high power terahertz sources and room temperature operable detectors. So it has a lot of applications in sensing, imaging, inspection, medical, defense, and that's why law enforcement and defense are very much interested in this. And it also has applications in communication. So now you already have 5G, 6G, 7G coming in, and that will actually enter into terahertz region of 600, 700 gigahertz and all that. So where this is very much useful. Basically, terahertz does not pass through metallic and conducting surfaces. So it passes through all the non-conducting insulating surfaces. So for example, it can pass through your clothes, and as a result, you can actually if you take an image of a person, so if he's hiding some weapon or something, so you can actually see in the terahertz image that what he is carrying. You can also use it for the medical purpose where these are the inner parts of the dental things that you can see, enamel and dentin and everything. So there are medical applications also of this. And these spectroscopy, what you can do with this can actually identify different types of molecules. So here I have given you these RDX, HMS, TNT, and all these explosive molecules. Similarly, you can have equivalent drugs that you can, contraband drugs you can identify because they have specific spectra. And if you can identify that, this becomes sort of a unique thing. It's like a frequency fingerprinting for that specific molecule. The other part is, of course, the material, the energy of this is in million volts, so you can actually use it for, probing, low-end dynamics in carriers. And you already had one nice talk by Professor Eric Fraze sometime back in this today's session. And you also have high-speed wireless communication. That's where Professor Ranjan Singh, who was he gave a talk yesterday, I think. So these are all the things that is happening because your speeds of transfers are going to go beyond 100, 500 to 1000 gigabits, that is 1 terabit per second. So the advantages of terahertz is that large molecules have rotational vibrational energy level. That's why you can actually identify them. And I already showed you that it transmits through otherwise opaque materials for the optical thing. But terahertz beam is extremely sensitive to water, and therefore it doesn't go deep inside the tissue. So you have to have very thin layers of biological molecules to do it because water actually is a main killer for this, and that's the reason you need high intensity terahertz radiation. So this limits terahertz radiation travel in the normal air because of this huge humidity problem. Especially in India, we do have this issue. So all our setups are always put up in enclosed in a box, and it is purged with nitrogen because nitrogen doesn't have any lines in the region that we are interested in, and therefore you can then study the terahertz very clearly. And you also need these tabletop terahertz sources of high intensity, but currently they are in pico, nano, or microwatts, so they are quite weak. And photon energy being so small, the room temperature is 26 MeV and your photon is 4 MeV. So if you want to detect an intensity, you need something, detectors which have to be cooled down to helium temperature. Kind of thing. Otherwise, you will get huge thermal background. So this is a typical spectra of this RDX, PNT, SMS, and you can see that there are very specific peaks, absorption peaks in this spectra. So all these can be used for frequency fingerprinting those molecules. And people have used these for imaging. So this is a image of the shoe back portion of the shoe, and if you are hiding some blades and other metallic things, you can easily identify. We also have this plastic explosive which can be identified in this images. And this is the photograph which is quite famous that this person is hiding his tool and also weapon in the back. And Terra can actually figure out this. So here I have basically put all the different power sources as a function of the frequency. And you can see that as you approach about in the terahertz region, they actually exponentially fall down the powers. And whatever high power sources which are available, like free electron laser, Felix, and gas lasers, and all that, they operate at one is a very single frequency, and two is for example, Felix requires a synchrotron, which is like few acres of land and that kind of machinery. Or you have these QCLs which are operable, they are quantum cascade lasers. So they have very high power lasers, but they have to be operated at like 4K or 77K. So again, it is highly high-end cryogenics is required, very sophisticated type. So again, it is very inconvenient. So you don't have something like room temperature operable things. If you also have gas lasers, which are quite old technology, but they also give you single frequency high power sources, but then there is the issue of stability and all that. So the photoconducting antennas actually lie almost at the bottom of this, but these are so far has been very popular because they are operable at room temperature as well as they are convenient and they are laser driven. So I will of course comment at the end of the talk about some limits. We have done some imaging of this leaf in the IFR, and you can see this leaf was put in the brown envelope, and then it was scanned through, and then you could actually see along the edges where the water is less, its intensity is high, and wherever there is a water content, you can actually mark those veins or water veins in the leaf. We had also done this imaging of this old 500 rupee note prior to demonetization. So you can see Mahatma Gandhi's photograph, watermark photograph in the trailer. So basically, the idea is we need sensitive, high power, room temperature operable, and reasonably priced detectors as well as sources, whether they are pulse or CW. And these will be all useful for imaging at the long range. So if you can demonstrate more than 25-meter long range thing, that would be a great thing. So in our laboratory, we have photoconducting antenna for power as well as for detector. We also have this electro-optic crystal which actually can generate using rectification, the terahertz, as well as we use it for detection, the bandwidth. And we also have these photomixers to generate one single frequency terahertz, which is used for doing very high resolution spectroscopy. We have also built this colorimeter which needs to be cooled to 4 Kelvin, up to 1.8 Kelvin you can go after pumping, and that is becomes a very sensitive detector of the terahertz. So we are all available in our institute at CIFR, and we have built these different setups. So these are all home built setups. So there are time domain spectroscopy that has a resolution about 4 to 7 gigahertz. The CW one has 2 to 4 megahertz, very high resolution spectroscopy we can do. We also do this optical from optical probe, time resolved reflectivity. We have also set up where we have optical from terahertz probe, but for high repetition rate, we did not get very uh, nice results. So we are now shifting it towards the amplifier one. And we have built this near field scanning terahertz microscope only of its kind in this country as well as I think in this part of the world. So you can do some wonderful things with that. So first, let us quickly go through these photoconducting terahertz sources. The basic mechanism is you generate with a optical photon, electron and hole pairs in the material, and you apply an electric field and you accelerate these temporarily generated electron hole pairs. And as soon as these beams get accelerated, you immediately generate a terahertz pulse. So basically, it's a current pulse which goes through. So we take semi-insulating gallium arsenide substrate, put these two electrodes, bias them, put this 10 or 100 femtosecond pulse of 800 nanometer, and then with that bias, it suddenly generates this terahertz signal. So this is basically the pulse work that has quite broad spectrum. But we can also use a similar idea. Only this, the design of this is a little bit different. This is called lock periodic antenna. Those who are familiar with this, they will know immediately identify. So you bias it, and in the center here, you put basically two, say 800 nanometer beam. So basically, you tune one to 799 and another to 801. If you put focus them here and bias it with normal DC, what happens is there is a carrier gating that gets created. So you have one some frequency and another one which is the envelope, which is the difference frequency. And that difference frequency lies in the terahertz region. So if you change this nu1 and nu2 with respect to each other, you can actually have this envelope of this current change. So this is like an AC current that you are putting it to the antenna, and that emits the terahertz. So we actually did the complete change tuning. So you can see that our devices are actually we actually made these this semi-insulating gallium arsenide, which is commercially available. That is really not a good material for the terahertz generation, but the good material, that is low temperature gallium arsenide, is banned for sale to India. So if you use the semi-insulating gallium arsenide even for CW, you can see that it is one order higher noise and is saturated. But with our implanted samples, where we actually implanted them to reduce the carrier lifetime artificially, we did this in our PIFR electron machine, and we could actually see that the devices that we made could actually go up to 1100 to 1200 gigahertz, that is 1.1 to 1.2 terahertz, with very high resolution in the megahertz order, tens of megahertz. Our other part was to basically, somehow enhance the efficiency of these sources. And the way you do this is basically you can modify the bulb. That is what we did by implanting. You can modify these electrodes, and as well as you can modify the region between these. So the region between the two electrodes can be modified because that's where the incident light has to be coupled. So we tried different kinds of designs which are plasmonic or photonic, as we call it. So one of these is shown here, where we did this circular hole kind of array. So these are all, of course, simulated first, optimized it, and then we, using E-beam lithography machine in PIFR, we have a clean room. So we fabricated these, and you can see the actual device that we fabricated. And side by side ones are the ones without any such design. So you can compare the whole structure with a non-hold one. And this actually, if you look at the IV curve of this, you will see that they are similar and it is independent of the polarization of this incident light. So we thought, okay, we may have missed something because the bias and the pump field are parallel and perpendicular is the same. But when you do the terahertz emission from them, they are remarkably different, and you can see there is quite a bit of a factor 4, 5 by each year, very different. So we wanted to understand why this was happening, and the reason was that when the bias field and the polarization are in the same direction, you basically generate these are the hotspots that we generate next to this whole structure. While in the when they are perpendicular to each other, you generate complete. There are no hotspots, so carriers can move freely without getting scattered. So as a result, your current pulse becomes quite broad, like the heaviside space function like thing, and therefore your terahertz emission becomes very weak. So of course we did the actual simulation. It's a very complicated simulation using console. We could actually take these sections of these, and using all of these, we came to this. So what I actually showed you is the result of all this very complicated analysis for both the perpendicular and not mean perpendicular and parallel biases. So these surface modification results are actually, you can increase this emission efficiency by making a photonic crystal-like structure. So what we had used it was basically dielectric, which is basically the gallium arsenide sort of surface, and air. So you have air, gallium arsenide, which is a dielectric. Now, our question was, can we replace that air by something else? And say, for example, metal. So now you have a metal and dielectric kind of thing. So here again, this work was done by Deepa. She's a phenomenal expert on this e-beam lithography. And you could see that this entire pattern was generated by her. Again, it's the same kind of thing. This is the ACM of that device, and you can see the beautiful pattern, hexagonal pattern of this gold germanium thing. And these act as a very good track for the incident light, as well as a very good tracking centers for the carriers that you. But once you bias it, it will quickly kill those. So we actually did the time resolved pump probe on this reflected, and we could actually see that the unpatterned carriers had 48 picosecond kind of lifetime, while the patterned one had about 30 picoseconds. So we actually saw a reduction in the carrier lifetime. And secondly, the current ID was actually was shown to be little bit higher. And so what we actually did was, when we looked at the terahertz emission as a function of the bias voltage, we could see that it was almost going by a factor of 2 or 3 kind of increase. And also when we looked at the pulse profile, the pulse had broadened a bit, and this is mainly because the here there was a reduction in the carrier lifetime. So it does. We were actually able to engineer this carrier lifetime just by doing this patterning. So we also studied some different types of patterns to do this. So the way this whole experiment was done was, we had to initially do all this pattern optimization. So you can actually see that these are all the hotspots which are getting created. So this is a theoretical simulation, and this was the reflectance spectra, and you can see the reflection is minimum at 800 nanometers. So this was, and our spectra was exactly incident spectra was exactly opposite to that. So we could actually optimize the absorption here of this carrier for this specific pattern. And this is the cross section of this whole this substrate. And you can see that there is quite a bit of intense intensity around the edges where the carriers get trapped, and that's where you could actually increase the efficiency of this. So we had also done this terahertz detector development. We had this irradiated ones, and we used different zinc telluride, gallium phosphide, gallium selenide based things. And we also had graphene fed terahertz detector, which can directly measure power at room temperature and all that. Only the bolometer works at low temperature. The other three are at So I will quickly take you through this. So what we did was we modeled it with the we used the same semi-insulating gallium arsenide which was implanted, and we made those patterns, and we actually also modeled them so that we can measure them for the current or not. And you could see that this is the actual terahertz pulse that was incident. It was used using the zinc telluride, and we characterize each of these samples with their carrier lifetime, use them in this model of this is where you generate the carrier, this is where you write the dynamics of that, and then the calculated and the measured current profiles are shown, and they match pretty well. So we thought that this was also pretty good. So this has been the total development. I mean, we have also done many more things, but I have skipped many of those due to time constraints. But we also went on to the study of different metamaterials. So out of that, the somewhat recent work what has been with the postdoc, Dr. Aruna Patnaik. He was doing my postdoc with me, and so this was basically the polarization control dual resonant terahertz transmission through asymmetric aperture arrays. So we made basically these different types of aperture. So if you have a slit-like thing, you get a different pattern, and if you modify it, make it little broader or shorter, you change this angle, and accordingly you will start seeing that the spectra and the resonances change, and you can actually see the simulated and the experimental ones, they match pretty well. So if you just have a single rectangular slit, basically the light that becomes incident on it, suppose the polarization is perpendicular to it, it passes through it. But if it is parallel to it, it actually gets stuck, and you actually are able to generate an aperture. So depending on the length of this slit, you will actually have resonance for that specific frequency. So you can see that there is a transmission, peak which occurs at this. So that is the reason why for that particular specific length and width you get this. So what we did was we actually we fabricated these samples and carried out this periodic array. So of these slits, these are all the specifics. So the idea is you will have one resonant mode which is for this cavity, and another resonant mode which is the cavity, which is the thickness of that, and they compete. And as a result, by changing this width of this for different tapering angles, he simulated and showed that there is a specific way that these modes actually come in. And this is also quite interesting in terms of having a periodicity can also affect this. So we decided to first study the rectangular part, just simple one. Not this is a bit complicated one because it's like a funnel, and there are you have electric field which is horizontally polarized or vertically polarized. They excite it in a different way, and so we decided that we will basically study simple rectangular ones, and these are the simulated graphs. Now these are of course done on computer, so we decided that why don't we do this using our experimental means. No experimental measurement and testing is possible in that. So we built this near field scanning terahertz microscope. So you have a tip here on which the detector is there, and this is exactly the same way. You can just assume that this is your photoconducting detector, and this is where this measurement of the terahertz is taking place right at the surface of this. So our resolution is about 10 microns. So don't confuse this between the nanoscope and this is a microscope because it will give you micron resolution. So this was basically done by Himanshu and Ajinkya. So Ajinkya is a expert on this. He really made a very nice looking. So here I can show you the time evolution, the way we measured it. This you will find that. All right, this is okay. This was not working. This is okay. I'll just get this part working in the end. But you will find that whatever this what measured here, you can actually see it in this, and we would like to extend it to these type of apertures because this is the kind of modes that we would like to measure. So for the rectangular one, we are able to do it. So we would like to do this for these type of things. We have also done work on this controlling dark quadruple modes in development structures. So it is like this kind of quadruple like you excite that actually kills this dipole, and as a result, if you just have a single dipole, you would actually see a dip here. Similar to the one which I showed in the previous one. But if you have these additional two bars, you can actually open up a window, and this is called electromagnetically induced transparency. So one can do a lot of physics using this, and we have also done different more polarizers or frequency selective polarizers, and you can see the measured and the numerically simulated experimental things actually match. We had also done work on these waveguides and etc. But that we will speak about it sometime later. So that has also been our another activity about the WGMR and all that. But that's a very separate subject, so I will not speak about that. So here in this talk today, we talked about the laser-driven terra sources, all of those devices I mentioned. There are limits due to its incident intensity, and there are multiple things. Even if you make them multiple size and everything, you still have low optical terra conversion efficiency, and also this thermal effect. So one has to really go for some other novel ideas, and you already know that Professor Sunil Kumar, who is the organizer of this conference, is also working on this syntronic related Terra sources, which they don't need biasing and they can generate a very large spectrum, really limited by the incident pulse. So there are a lot of such activities happening in India. So ours is basically the biased one and photoconducting based semiconductor. We use normally semiconductor. So our current research and for future, basically, of course, I have just given you some glimpses of our results from this year. Carry microscopes of only its kind in this country, and we are getting now new results. So we would like to extend it to these biomechanical molecules. We are also working on the analysis algorithms for this Terra's data. We also work on history gallery board studies. So some of you who may have attended our ULC conference this year, January, would have known our work on that. Then we also study the crystals for generation, detection, etc. And we would like to extend our thing with high field terahertz. But because of this corona, we could not get into this, and we study on the magnetic field. So we are going towards that. And final aim would be to develop this nanoscope using SPM. So that's a dream. So let's see. So I wish to thank all these people, Professor Gopal, with whom I share my lab. Thanks to him. Abhishek Singh is doing postdoc now, and funding from BAE. And these are all the collaborators who have helped me at various times. So today's work I talked about was these three people, Arnab, then Himanshu, and this guy, Ajinkya. He's still an undergraduate, by the way. He's a master's student and he's a postdoc. So, these people have worked on WGMR, Anshri, and Devanshi, and Dhruval, but there is something else. So I would like to give credit to them. So thank you so much. I think the talk is now open for comments and discussion.
Yes.
Oh, sorry.
Thank you, Professor Prabhu. So any question? Maybe we can take one question, question from the audience. Yeah.
Sir, here is Vikas. I am wanting to ask one question. Sir, you have shown the metamaterial of that particular conic section. You have just shown the basic unit cell of that also. So can we do some kind of we are arranging in it one directional? If we arrange it period by period in different directions, so means anti-parallel 2 and 3 unit cells row are basically in one direction, then another 2 and 3 unit cells in other direction. So can we do in like beam steering purposes also, beam shaping purposes?
Yes, is this the one that you are talking about? This shape or the
This
whole?
shape, this conic shape, this cone shape, basically. This
No,
one.
this cone. Okay, this
Yes,
cone shape.
sir.
Yes, you can actually do it. These are all done here only in.
So my main question was why this structure has been selected like this conic section one, funnel shape one.
That is because we wanted to study how the dipole of this, see how its frequency gets affected. So here, see, here if you go on changing the tapering angle, the frequency lowers. But if you, for different, see, you see these two different trends for two different polarizations. You would have expected the same trade, but here there is a blue shift. Upper one is showing blue shift, while here it shows a red shift. So we wanted to study why this was actually happening and how these modes actually affect each other, the cavity modes as well as the modes which get generated using this. So we came up with this. Of course, the simulation tells you how this works. So you do get weaker and stronger dipoles. Accordingly, you can you can explain all these features, how that works.
Okay, sir. Fine, sir. Thank you, sir.
Okay. So thank you, Professor Prabhu, for a nice talk. And of course, I mean, if the participants or people who watch this video or who are watching this video on YouTube link, if they have some doubts, then will be can direct the questions through emails directly to you. So thank you again for a nice talk.
Yeah. Thank you so much.
Thank you. So now we move to the last talk of our terahertz and microwave session. It is by Professor Rajiv and Kinney from Icee, Thiruvananthapuram. So,
Hi,
Professor.
Rajiv.
Yeah.
Hello, Rajiv.
Rajiv, yeah. So, Rajiv, you are here already? Yes, Rajiv is here already.
Yes.
Great. Yeah, so Dr. Rajiv obtained his PhD from IIT Madras, and then he spent few years for postdoc. He was in Virginia Tech and National Renewable Energy Laboratory, USA. So he is with the Icee since 2010 and has been working in the areas of terahertz related science and technology, ultra-fast optical studies of different materials. He has received quite a few awards. Some of them to mention is Kerala State Young Scientist Award and so on. So today he is going to tell us about the recent work that his laboratory is working on, and that is basically on the terahertz spectroscopy for fundamental science and industrial applications. So this is the title of his talk. So over to Professor Kinney now.
Thank you, Professor Sunil, for the introduction and also the kind invitation to present our work in this conference. So, is my presentation visible?
Yeah.
So, I'm going to talk about two aspects of this terahertz spectroscopy, wherein I'll show you two examples, one from very basic fundamental science application and another one industrial applications. So before I start, I will, the system that I'm talk about is one is actually a charge density wave material, which is actually a spin ladder compound. It's called strontium copper oxide. It's also called telephone number compound, because as you can see, it's 142441, strontium 14, copper 24, oxygen 41. And so that's the number, that is 142441. So that's one system which we have studied using terahertz spectroscopy. And I've tried to give a flavor of what we can do on such compounds on this. The other application is actually entirely, application oriented, wherein we use terahertz spectroscopy for the evaluation of thermal barrier coating. So I will try to explain each of these in detail. Before I go into it, I should give credit to the guys who did this work. So the first work on the spin ladder compound was done by a PhD student, Saudra, and the samples were grown in either Pune by Rabindranath Bagh and Surjit Singh's group. And the second part of the work was done by a couple of students. One is an undergraduate student, Vivek Vijayan, who has just now gone to Germany for his PhD. And one of the PhD students, Vivek Vaishag, and who is now doing a postdoc in Parag. And Ria, who is currently a project fellow in Micro. Okay, so Professor Prabhu has made my life easier because he has already given the introduction to all the techniques and the terahertz things. So, I will actually skip through a couple of slides. So I was planning to give an introduction about terahertz spectroscopy and its applications in condensed matter, atomic and molecular physics, and material science. But I think I can skip this because Professor Prabhu has already talked about it, and he has also talked about applications wherein you can actually detect things hidden behind an opaque barrier. And he already talked about semiconductors and terahertz radiation. As you can understand from his talk, that semiconductors and terahertz radiation has a very unique bond between them, because one can use terahertz semiconductors for generation of terahertz radiation, and conversely, you can use terahertz radiation for studying these semiconductor materials and different materials. Professor Prabhu also talked about photoconductive antennas for generation and also detection of terahertz radiation. So that also I can skip. So my main aim here is to look at materials under terahertz light. What happens to them, or what is the things that we can learn by putting them under terahertz radiation. So as I said, the first system that I'm going to talk about is telephone number compounds, strontium 14, copper 24, oxygen 14. This is actually a layered material which has a layer of copper oxide chains and a copper oxide ladder, spin ladder. And these two layers are incommensurate, meaning incommensurate along the c-axis, meaning the lattice constant is different along the c-axis for the chains and the ladder. So they are structurally incommensurate, and there is between these two layers there is strontium atoms, and intrinsically there are about 6 holes in this material. So it's a hole doped material. Because the chains are slightly flexible, they buckle, and in a sense, this buckling gives rise to what is called the charge density wave. So the charge mode gets modulated in this fashion, and because of the charge modulation, a gap opens up, and this gives rise to a charge density wave, and due to that, a gap opens up in the energy spectrum. Okay. Now this gap is in the milli-electron energy, and one could use terahertz for studying this. The way conventionally to detect this is actually this material is a little bit complicated, and it doesn't undergo a metal insulator transition and cool down, but it goes from a normal insulator to a charge density wave insulator as it is cooled down, and this happens at about 165 Kelvin, and which is what the charge density wave transition temperature is. Okay, so if you do the resistivity versus temperature measurement, you could see features related to the charge density wave formation in that. Now, this has been observed and this has been studied for a long time, and it is understood that the gap that opens up is about 116 to 130 MeV, and but still the spectroscopic features related to the charge density wave mode is not very studied well. For example, in one paper by Kitano, it was suggested that the charge density wave mode appears in the hundreds of gigahertz region. Later on, came, which said that charge density wave mode occurs at 360 to 400 gigahertz. And but they themselves in a later paper assigned this to a mode due to the pinned charge density wave. Okay, so there is ambiguity in the charge density wave mode, and we did a study on this, and I will talk about it. So as you can see, when you have the modulation of charges, it has 2 degrees of freedom. One is the amplitude on wherein you can actually modulate the amplitude of this, and another one is the phase of this. You can modulate the phase. So the phase modulation gives rise to the phase on mode. The amplitude modulation gives rise to the amplitude on mode. Now, the amplitude on mode behaves more like an equal to 0, and it is more like an acoustic mode. But in this material, as I said, it's an incommensurate layers and chains. So this gives rise to a lifting of this phase on mode. So it is no longer 0 at Q equal to 0, and that is what I'm going to actually talk about. Now, this chains and ladders, as I said, there are 6 holes intrinsically available in this material, and this is distributed between the chains and ladders, and this makes the chains negatively charged and the ladders positively charged. And when you have when you excite this, you have a sliding motion of these two, and this gives rise to gapped phonon modes. And these phonon modes they occur in the 300 gigahertz range. Okay, so there you can observe 2 kinds of spectroscopic features in the terahertz region. One is this sliding phonon modes. The other one is possibly the charge density wave phase on modes. Okay, so another signature of this charge density wave, the sliding phonon modes is seen in the specific heat measurements. When you actually do the specific heat measurements, what we see is a bump at about 10 Kelvin, and this 10 Kelvin bump and 10 Kelvin corresponds to about 300 gigahertz, and so there is an increase in the specific heat due to this sliding phonon mode. Okay, so as said in the previous talk, you can actually generate terahertz radiation using a photoconductive antenna, and also terahertz radiation can also be generated by exciting ultrafast excitation of a semiconductor. Okay, so in this study, what we have used is a simple excitation of a low temperature grown gallium arsenide with a little bit of bismuth in it. So there is no photoconductive antenna, but it's just a bare semiconductor epilayer. And detector, we have used a photoconductive antenna, and the samples were mounted on the cold figure of a closed cycle refrigerator. And this whole terahertz setup is a simple home built setup, and we have a box around it, and we purge the whole setup with nitrogen gas to keep the humidity levels low and absorption due to water vapor. Now, as I said, we have used gallium arsenide with a little bit of bismuth doping in it. And what this came out from some of our previous studies, where we had observed that adding some amount of bismuth to low temperature gallium arsenide increases the efficiency of terahertz radiation. As Prabhu might have mentioned, the low temperature gallium arsenide is the most commonly used material for terahertz emission. and if you add a little bit of bismuth to it, you get a higher emission intensity. And the reason why we used this base is bare semiconductor instead of photoconductive antenna is that what we found is we get better spectral features in the semiconductor based instead of a photoconductive antenna one, probably because we get lesser electrical noise. So for example, here I show the terahertz spectrum of BBO, terahertz spectrum of terahertz signal that has passed through BBO crystal. And you can see that when we detect it, or when the terahertz is generated using a semiconductor, we get the terahertz absorption features much clearer compared to the dedicated photoconductive antenna. So this is a comparison here. It's not gallium arsenide, but it's a gallium antimony bismuth, but it conveys the meaning. You can see that we get much nicer features in the spectral studies. So hence we have used this bare semiconductor. So now when we actually did this terahertz measurements on this layered compound, which is this spin ladder compound, this is actually the terahertz signal that we detected after passing through the sample. Okay, so one thing that you would notice is this very fast oscillations that you see, and the period of this oscillation is about 1 picosecond. And on top of that, you also see a very slow kind of oscillation, which is about 4 picosecond, which is clearer at the higher temperature because there is no longer this slow oscillation. So there are two kinds of oscillations that you observe in this terahertz transmitted signal. With the gallium, low temperature gallium arsenide generation, just for comparison, I also show the interdigitated photoconductive antenna signal. You can see these fast oscillations are there, but it's still better in the low temperature gallium arsenide bismuth one. Okay. Now, what are these these oscillations coming from? If you actually Fourier transform this, and I have put the spectral spectra of the reference signal also. As you can see, the sample is blocking a region between 0.25 terahertz and 1 terahertz. So that gives rise to a peak in the transmitted spectrum. The peak occurs around 0.25 or 0.3 terahertz, and that 0.3 terahertz is giving rise to this slow oscillation. And again, this upper cutoff region gives rise to a peak around 1 terahertz, and that 1 terahertz is giving rise to this fast 1 picosecond oscillation. Okay. Now, what is the origin of all these things? So I have two dips in the transmittance. As I mentioned in the beginning, you have sliding phonon modes because of the sliding motion of ladders and chains past each other, and this as can be seen in the specific heat measurements at 10 Kelvin, which corresponds to about 300 gigahertz, and that is giving rise to the first dip at 0.25 or 0.3 terahertz. Okay, and this oscillations and these features you see only if the electric field is parallel to the c-axis, and if you go for measurements with the electric field parallel to the a-axis of the crystal, you don't see any oscillations, and that actually confirms the anisotropy of this material. Okay. Secondly, if I concentrate on this fast oscillations, you have this fast 1 picosecond oscillations. Here I am showing the same oscillations as a color plot. As a function of temperature, as you can see, these oscillations disappear above a temperature which is about 164 Kelvin, which matches with the charge density wave transition temperature. Also near to that charge density wave transition temperature, the oscillations undergo a phase change. Okay, and if you take the transmittance of this, you can again see that above the charge density wave transition temperature, this cutoff is not there, and it is not transmitting at all. but below that, it is transmitting about 1 terahertz. Okay, and so this, matching with the charge density wave transition temperature tells us that this 1 terahertz, 1 picosecond oscillations has something to do with the charge density wave. And if you dope it with cobalt or aluminum, these features are completely gone, which is the fast oscillations is completely gone, which is because the charge density wave is affected by cobalt and aluminum impurities, because they dope the ladder, and it is in the ladders that this charge density wave is formed. Okay. So if you convert this the transmittance into the conductivity data, you would see that there is a peak around 0.96 terahertz, which is due to this the fast oscillations, and the second and also a lower one, which is due to the sliding Coulomb mode. So in effect, what we have seen is the sliding Coulomb modes, which actually corroborates with the excess specific heat measurement and also signature of the charge density wave mode around 1 terahertz, and aluminum and cobalt doping destroys the charge density wave ordering, and hence these oscillations are dissipated. So that is one part of the talk where I wanted to show you some application of terahertz spectroscopy in some basic science problems. Okay. Now I will take you to the next problem, which is non-destructive evaluation of thermal barrier coating. As in the introduction, this terahertz is transparent to many materials, including ceramic. So most of this turbine engines, which go through a lot of thermal cycling, are coated with ceramic materials or ceramic coatings, which are called thermal barrier coating, to protect the underlying metallic or alloy material. And this terahertz is also transparent to these materials, and hence we can use terahertz spectroscopy for evaluation of these coating layers, because the coating layers, the integrity of the coating layers is very important, and to maintain the integrity, it is very important. So what we can do is, if you actually set in a pulse of terahertz, since it penetrates, a portion of it gets reflected from the top surface of this thermal barrier coating, and it penetrates and it gets reflected from the next interface. It could be a layer called bond coat, which is actually used to adhere this thermal barrier coating to the alloy material. So you will have a reflection from that. The bond coat is more or less like a metal, and then there could be multiple reflections, and you will get a signal which has actually multiple peaks like this. Now from this, one could understand the thickness and other properties of this thermal barrier coating. For example, if this thermal barrier coating has degraded and the thickness has gone down, what should happen is the reflected pulse, these pulses come successively are called the echoes, and the time period between these two, between the pulses, is actually proportional to the thickness. So if the thickness has degraded, time between the two pulses will reduce, and hence from that one can understand what is happening to this. So here is some signals wherein this is the first one is just from a bond coat, which is just like a metal, so you have a single reflection. But when you have a sample which is just grow out, you have multiple reflections. And for example, you can actually take it through different heat cycles and look at what happens to those materials as you heat it. So one of the problems that we looked at is actually when you take this thermal barrier coatings through thermal cycling, thermally grown oxide layers grows between the TBC layer and the bond coat, and whether we can actually detect this. So one can actually apply Fresnel's reflectance laws and figure out what is the percentage of signal that should be reflected and for the intensity in each of the echoes. Not only that, the surface profile, most of the time, these have roughness of the order of a few microns. And as you know, the terahertz also has wavelengths in the micron region. So one has to actually take into account the surface roughness, and that also can be integrated into the calculation. And one could come up with a transformation matrix where it can actually give rise to the multiple reflections. So we simulated this whole signal using a program. Okay, so here is actually a terahertz signal that we obtained from a turbine blade sample, and the red one shows the simulated signal trying to optimize the parameters. So from that parameter optimization, one could obtain the refractive index, the thickness, the surface roughness, and so on. Okay, and another thing is that I'll just briefly say is that when you have actually multiple reflectance, this would be very similar to what is called the K6 oscillations in X-ray diffraction, and one could also use this information to figure out if the thermally grown oxide layer is present or not. Okay, so I will. So this is a simulation wherein one could even detect very thin layers of thermally grown oxide layers, even up to 10 micron using terahertz spectroscopy. So with that, I'll come to the end of this talk. So as I said, whatever we did is using one of these kind of setups where you have a huge table, and on top of it you have a very large laser setup and so on. But the idea is to actually apply this into on a turbine blade or so. So I cannot take this whole setup to the field, neither can I bring the turbine engine to the lab. Okay? So how do we go from there? Can you actually find a solution which you can apply on site? Okay, so that's the future direction for this problem. Okay, so with that, I will stop, and thank you for.
Thank you, Professor Kenny, for a nice talk. So now this talk is open for maybe a couple of questions.
Hello, sir. Here
Yeah,
is
Vikas,
Vikas. Basically, you were telling me basically you were telling about these telephone crystals, telephone basically
telephone
compounds,
number compound.
and
Yeah.
telephone number compounds, and these telephone number compounds has a special property that phonon modes gives rise to various bands. So also there are other. Yeah, acousto optics properties like you have shown. Yeah. So we are getting some different feature from these compounds, then it will be very good. So I want to know just that particular property, because people are using this cesium iodide also in the far infrared region.
Because your question is not clear. Can you repeat again?
Sir,
Or you can
basically
actually put it in the chat
yes,
box.
sir.
Yeah.
Sir, you
Because
have shown the phonon modes basically in the telephone number compounds. So there we are getting various band properties you have shown there, like these
okay.
basically Fourier spectra also. So these properties are basically facilitated by some other materials like cesium iodide in far infrared region. So is there any special feature which we can ensure in these compounds for getting these applications, acoustic applications?
Because, but the thing is actually, the more that you are looking at, right? If they are in the terahertz region, that's depending on the material, isn't it?
Yes, sir. Yes, sir. Yes, sir.
Yeah. So if they are in the few terahertz region where you have a good signal, then you would definitely be able to see that.
Okay. 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 Yes, sir. Fine, sir. Thank you very much, sir. Yeah.
Thank you.
Is there any other question? So Professor Kinney, you have this temperature dependent measurement in the frequency, I mean terahertz frequency. So you have an optical cryostat?
Yes, that's right. Yeah.
Integrated inside the terahertz spectrometer. That's great.
That's right. Yeah. Yeah.
Okay. Very good. Very nice work, Professor Kinney. And
Thank
yeah,
you.
so if there are no
thank
further
you.
questions from the audience, yeah, so thank you, Professor Kinney, and thanks to all the invited speakers who could spare some time to talk in this conference. So thank you very much, and see you again sometime soon.
Sure, sure.
And
thank you.
yeah,
Thank
so
you.
there is, yeah. And now a small announcement. We now can move to the post-session ceremony that is going on in hall number. Vikas, can you tell me what is the hall number where this ceremony is going on?
I think it is in hall number 1. I'm not sure about it, but
Okay. So
Sandeep,
yeah,
can
so
you
we
tell
can,
me? Yes.
right. We can look at the schedule,
Yes, sir.
the details there, and now we can actually move to that hall. Okay. Okay. So thank you all for participating and contributing. Okay. So see you again sometime soon, and bye bye from our side now.
Thank you. Bye.